For some reason, this one stopped also this morning. I don't know why. When I went to switch it up, it was already off for lunch.
Interesting. Did you eat lunch?
I went to Macy's
Did you? Huh?
alone.
Did you find anything?
Yeah, I ate a very nice soup.
Oh, good. That's a good idea.
Veggie soup.
Yeah, that's a good idea.
Lay down on the grass
Okay.
for 15 minutes.
Sorry for both.
You get it off. All right. Excellent. Okay.
Should be right here.
All right. So welcome back from lunch. We've got a full set of talks this afternoon, and kicking off will be Bob Dean. You guys need to support a medium-term archive.
Okay. Y'all hear me?
A little higher. Maybe a little. Oh, is it on?
Okay. How about now?
There you go.
Yeah, okay. Well, I guess the job of the first person after lunch is to put everyone to sleep, so hopefully you'll avoid that. Anyway, this is intended to be a thought-provoking piece. You know, I'm not necessarily espousing any answers here. I'm just posing a question. Here, PDS is a long-term archive. You know, we're talking 50 plus years. That's that's the entire reason of existing. And so its holdings are fairly limited to static data. Flight missions provide a lot of services while they're active. There's servers, there's databases, there's interactive mechanisms. You could call that a short-term archive. Archive's not the right term here, that's why it's in quotes. But during the mission, often just to the mission people, science team or whatever. And 6 to 12 months after the mission ends, the missions get closed out, servers go away, and these things are not available. So there's nothing in between these extremes. You have 50 years and you have maybe a year. This is a medium-term archive, 5 to 10 years. So these kind of services that I'm talking about are, still be of benefit after the mission ends. Data access and processing and such. So first I'm just going to run through some examples. These are just ones that me and my co-authors are most familiar with, but there's plenty of others. That's our tool that displays data. It's works on Java, JavaScript, iOS clients, uses a server, data visualized in various ways. Places, that's our database of rover localizations. The data itself for places is put in PDS now. The server provides a lot more capabilities in terms of coordinate system translations and maintenance of user-created localizations.
It's not loading.
This is a tool that's used by the mission planners to command the instruments, basically. Obviously, there's no instrument commanding after the mission ends, but visualization component to the tool, which could still be used. MMGIS is a threats tool. It's a GIS system that puts all your data in context with a mission base map. And so you can see geological context of where all these observations come from. That's a service that provides enabled access to resources and gets you things like, label access to label items. JMARS, JMARS tool that has a wide user base, developed and maintained by Arizona State. So, you think, hey, they're still supporting it, and as far as I know, they're going to support it, for quite some time. What would happen to it? If ASU just decided, hey, we're not in the JMARS business anymore, what do you do? This is our image processing suite. And really, ISIS is in the same category. Vickers, is 50 years old. We're continuously maintaining it. We use it. And as long as we keep using it, it's not a problem. But if support for that ever terminated, or if USGS lost funding for ISIS, or who knows what. CNUM's data server, this is how for their MIMS observations. Calibration is on the fly based on user parameters. Titan Browse, similar tool to look at radar data from CNUM's data for Titan and other instruments. So, these all have some features in common. There's basically an active server or active code that has to run somewhere. Software tends to rot over time. It's a well-known phenomenon called bit rot. Hardware becomes obsolete, CPUs change, time scale. Things back in the 1980s, when I started JPL. Dedicated frame buffers for image display. 9-track tape drives. Box of those under my desk still. CPUs change. None of these are currently available. Compilers change. Language choices. Pascal, Ada, COBOL. You rarely see those anymore. Some KNRC from the 80s doesn't compile now. Networks evolved. I mean, there was no network, way back in the day. Anyone remember DECnet or BitNet? I mean, change. MS-DOS, CPM, VMS, OS 360. Even on the same OS, you have compatibility problems between different versions. The problem with software is that it's unlikely to work in the future, and certainly not. There's to stand here and say, hey, we're going to archive software for 50 years, and everyone will laugh at you. 10 years, is that feasible? Virtual machines, I think, give us a very good way to think about this. They preserve a given operating environment. They can help make old environments available for longer. And of course, the file formats are kind of in flux and not standardized, and they still be readable in 50 years. That's a question. So, why? Well, I think that the majority of science results come within 5 to 10 years of the mission end. Before mining really old data, getting good stuff out of it. But I think the low-hanging fruit has been picked by them. Of course, if you're doing change detection, or if your spacecraft goes back to the same spot, you're very interested in the data again. But that's exactly the kind of time frame we're talking about here. This gap, I don't even know what the PDS is doing. Now, long-term is vital. I'm not in any way saying that the long-term aspect of the PDS be de-emphasized or diluted. I mean, that is absolutely critical. Long-term users can't be any worse off than we are now. We have you have the static data, it's out there, it works the same way as before. The medium-term thing simply provides more options. So if it is available, if you're within that time period, it's easier to work with the data. users may benefit as well. You know, the source code may be available, even if it doesn't run anymore. You can look at that source code and shed some light on what was happening. And if the future mission goes to visit the same body again in the future, you know, you have a leg up on maybe resurrecting these services. So how might this work? Answers for closing questions. Kind of the, you know, our thought is that activities would include packaging these relevant servers and software into VMs. Yes nodes, the relevant ones, would deploy these servers and simply keep them running as long as they can without too much investment. Now, they can't maintain them forever. That's really expensive. I mean, if it's something trivial, you fix it. Okay, great. Parties could update it if they choose, but at some point, it breaks, the node simply turns it off. You know, it's like, we're not saying we're guaranteeing that this stuff is going to be available. We're just trying to make it available as long as we can. Part of the thing that helps with that is there's no new data coming in, so all the ingest subsystems of these tools. But simply keeping the power on is really helpful, because after nobody's paying the bill, you know, you can't, there's no place to host a server just to do the same thing. So there are some precedents. The imaging node has already deployed the Java Mars Viewer client and the servers that it needs. Now, this is a actually supported server right now. I mean, we're actually supporting it for other missions inside Phoenix, actually, in 2020. And so it is being actively maintained, but it's an example of, here's a service, the PDS node, that, you know, is going to be around in 50 years. Vector image processing system. It's been under continuous development for 50 years. I mean, we had actually had our 50th birthday last year. I don't know if you guys realize that. Generally, when a mission ends, you know, we don't, it's kind of a benign neglect thing. It just sits there, keeps building. If it stops building, it becomes a problem at some point. But that concept has proven to be useful just because it preserves the old code as long as possible, and people need to use it if they can. So, summary, I think, you know, we feel the answer is yes. We do need some kind of archive. Archive is not really the right word. You know, some way of maintaining these services over with little investment and just until they stop working. If they stop working, you know, or the security hole that people can't handle, whatever, turn it off. You know worse off than you were before. Things happen. You tell us. Thoughts?
I'll just try to ask. Bob, I'm curious if you've tried to prototype putting any of these tools in a virtual machine and let some people try that as provoke interest in doing something like this?
We have not. Part of the motivation for this was a poster that Chase had last time at this conference on software. Right after me, and we addressed some of that. Some of the more nuts and bolts. We, you know, we didn't coordinate our abstracts, but they're similar. That's a good idea, and that's something that, you know, basically I'm just trying to start a conversation. So.
It does stay on. Okay, I'll project then. Just a comment really, I think in addition to the benefits you've already listed, that having the software still running after the mission means when similar along in the future, they could maybe start without not having to start from scratch if they already have some capability there.
Oh, thank you. Did that make sense that they could use the server or software that's already there and build and extend it instead of having to try to figure out how did that thing work in the past? Let's try to do that again.
Absolutely. And I think if the service is still running somewhere, that makes it a lot easier. But even if it stops running, the source code would still be there. You can still look at it and figure out what's going on and either rewrite it or update it or do whatever case to bring it into the second century.
And just as a final, I will say this is one of the challenges that will be discussed on Thursday again is at the map set of what is this medium-term archive. So if you do happen to be around on Thursday, it'd be good to get input, especially, we know that this is a problem.
Yeah.
Right? And so I think, and I was able to actually stand up maps that I think they understand the problem.
Next speaker is Chase Millian talking about the status of software preservation in planetary science.
Hi. So the following things I'm going to assume and only defend them for this one slide. That research software should be preserved because it is expensive, and when all of our data is digital, it's indistinguishable from the method. Also, that preserving source code and documentation, while necessary, is insufficient, and that's because getting the code to run without the context, that's the operating environment, and understanding its functionality without being able to run it, very, very hard. And also the function of software is often not obvious from the source code. You have to look at it. So it is true that not all software can be saved. Will be lost. So I'm not proposing. I'm not proposing that we try to save everything. I realize that's impossible. And if you want to argue with me about this, I love talking about it. Since the last workshop, I gave a poster that said basically we should share code, and if we didn't establish our own policies, they would be imposed upon us. To come to pass. Since the last workshop, code sharing has become a requirement for some programs, particularly PDART, and the ROSE's DMP, the Data Management Plan language, is much stronger with respect to requirements for software. Planetary science in particular, there seems to be more recognition that code is a first-rate research product, certainly a very important one. So the PDS has clarified their policy with respect to software archiving, and that's the text here at the bottom. Source code that is sufficiently documented may be submitted as documentation or an example of some processing algorithm. This clarifies mutable digital data or running software is not welcome in the PDS. Appropriate, and I'm glad to have it clarified so that program officers won't keep telling me to put my software in the PDS. 1617 guidance on software includes this language. I've highlighted the red things that I think are important, which is that your DMP should cover any other data and software that would enable future research or the replication, reproduction of published results. And I think that insofar as the software is the method, this covers software, and insofar as just code is insufficient to meet this requirement. You also need documentation sufficient to enable the code's reuse, which is again the software. And importantly, a lot of people are worried about this. NASA does not expect you to maintain your code after you release it to the community. So there's no unfunded work expected of you on that count. Also, PDAR this year usefully defines a PDS equivalent archive. That is, you must archive your data in PDS or PDS equivalent. That has the following properties: independence, sustainability, open accessibility, reliability, agreement, standardization, peer review, and documentation. And I've written next to these how close I think we can get, not how close the PDS is, but how close human beings can get right now, and I'll go through them. Right now, no software archive that meets these requirements exists anywhere on the planet. The closest examples archive video games. There's certainly not a software archive that meets these. First of all, sustainability, which Rosa defines as 25 years. The PDS generally, I think, uses 50 years. No one can guarantee this with software for the reasons Bob just mentioned. I think that 10 years is probably feasible with virtual machines. And most people ask, well, virtual machines rot too. You can do what I call nesting, where you put virtual machines in more virtual machines. And you rely on market forces, particularly people run their servers in virtual machines to maintain some continuity there. Example of this, which is ISIS-2, which last I checked had functionality that only existed in ISIS-2 and was critical, for example, Cassini data analysis. And there are people running ISIS-2 in like 3 levels of virtualization in order to get to that functionality. 50 years, however, might be feasible with something called a universal virtual machine, which is basically a virtual machine on a universal Turing machine. Crazy, it's the kind of idea that gives me vertigo, and it doesn't exist yet, but it's potentially the turtle at the bottom of the stack there. Also, open accessibility. Software licensing is really complicated. And also software can be ITAR, EAR covered, which is not a problem that you have with observational data. It's analogous to copyright problems they had for the Google Books work, but it's like 100 times harder. And I've talked to people who worked on that initial Google Books work, that seems to be intractable. Future, any software archive is going to have to be data restricted, which means it can't be, or access restricted, it can't be the PDS. Searchability, you can just search software, but then there's this important question of how do you know if what you're looking at is what you want? It's a technology called the Olive Executable Archive, which I just do. It's basically YouTube for virtual machines. You load up the website, it streams as you work the virtual machine. So you don't have to download the virtual machine, it just works instantly. Computer. Who built Andrew File System, and also Gloriana St. Clair, who did the Million Books Project, which was the precursor. A few years ago, this was hard, but now it's very easy. Lots of ways you can get document object identifiers. .NET Astrophysical Source Code Library. That planetary software is welcome there, and that is eager to have more planetary scientists submit their code there. And also citation tracking services now track software. If you're not citing software in your papers, please start doing that, because a lot of us mostly produce software and we want credit for that. Finally, peer review and documentation. It's not clear what peer review of software means. What do you optimize against? Is it quality, coverage? Does it never break? It's important to understand what we want to review for before we move the software, and that's not at all obvious to me. As peers of software, is it scientific end users, is it other programmers, users who are not programmers be able to review the software in the way that you want? This is just a comment that I know every programmer agrees that nobody else has enough documentation. So I think the one thing will be documentation for software. And this is relatively new. The Journal of Open Source Software has been around for less than a year by Arthur Smith, who used to be at GitHub. He's now at Space Telescope. are sort of a trailblazing effort in what it means to have peer-reviewed software, little one-page papers for your software, and then a couple other people review it, and you get a citable index. And then it's preeminent standardization. These were all things I listed as solved on the first slide. There's someone to do it. These are better as well, but they also require money. So someone's going to stand up and say who's going to pay for this. I mean, NASA wrote it in the law, so they probably should. Side, a lot of people say archive your software in GitHub. The NASA Rose's proposal uses that language. People earlier in the day use that language. Archive, it is a project management tool, and this point was relatively obvious. I think it's obvious to archivists. GitHub lacks the properties that any serious archivist would find to be non-negotiable. But yet a lot of people who I really respect keep bringing up this point. So I'm rethinking my argument. I don't think I'm wrong. I just need a better argument. So if you bring this up later, I won't be able to defend myself, but maybe in a few weeks. Finally, for data management plans, when I work on proposals, this is what I send to my PIs and co-Is. And I encourage you all to use it if you want. The standard should be in data management plans. Basically, it says that you'll preserve all of the software. You'll preserve all of the source code along with documentation. Importantly, that red section is the most important one. Thing that's necessary to reproduce your published work, because that's really what I want to be able to do. Legal and feasible to do so, you'll preserve virtual machine images somewhere. There's not a real place to put them right now. So if you just preserve them, I'll be very, very happy. A lot of your institutions will have archives that you can just drop these in. They'll be access restricted, so you don't have to worry about licensing. In summary, this was told to me by an old archive who was around during the Google Books fiasco. The archive community was sort of crippled in fear about the copyright issues. And his advice to me, and I've forgotten his name, I'm sorry if he's watching this, was while you're talking about the software archiving issue, do not let perfect be the enemy of good. And I see this a lot. The question is not whether we can save all the software, whether we can archive it perfectly. It's that software is constantly just dying with as much of it as we can, with whatever means we have available. So momentum continues towards a good solution. We can do pretty well with what we have, but not perfectly. Archive to the PDS standard. If everyone in this room, most of you write software professionally, if you just committed to preserving your software in some form or insisted that your employer allow you to do so, I believe that would be a huge deal and we would save a lot of software that way. It would also serve as an example to the rest of the community. And Bob and I arrived independently at this same conclusion, which is that the PDS is not an appropriate place for software. Any repository where we put software, we might not be able to call an archive, but we do need some sort of standard solution for the community, for NASA-wide, and there's will be the first in the world, which would be great. Thank you.
I just have a couple of comments. Speaking as a PDS person, I agree with you wholeheartedly that it would be very helpful to have such an archive-like site. I know from my own personal experience that some of the tools that we have developed in astrogeology, we've gotten funding eventually from from PDARC or Laser or some other. Our most recent tool, it took 3 iterations through a review panel, but I know that PDARC, for example, is asking for software for products, but I believe they are also asking for tools that solve problems in PDS. And I think this your argument is good that PDS is not necessarily the answer here, but I think this kind of thing could well be proposed to PDAR. And it may take a time or two, because as what has happened in my experience is there's a little groundswell, a recognition in the community that needed, and now is the time for it. It might take a year or 2 or 3 to get to that point, but I guess I would encourage you to try something like PDAR. That one in particular, that program in particular does ostensibly support aspects of PDS in terms of requesting for those kinds of proposals. So, one possibility.
Ross Byers, Study Institute, NASA. So I think you should stick with your argument, not to let people call it archiving in GitHub. Even the PDS, as Lisa indicated, doesn't think that archiving is the right word for software at this stage. And in fact, we've recommended to NASA that the next roses not use that term, but instead use the word in GitHub, right? Deposit your software. That's why the archiving which implies this. Thanks.
Okay, so our next speaker is Steve Hughes about PD4 tool development, leveraging the PD4 information model. I think maybe you'd say part 2. Is that right?
I talked, both actually Dan and I were talking about the way the information model is to drive the information system, the infrastructure, the tools. And so this talk will start kind of giving us an overview of how that might be happening. Sean Hardman, Jordan, Mr. Jordan, also Custine, I didn't get Custine's name on there. People who are actually doing this, they're using the information model in various ways to develop software, services, and systems. This talk. So this slide, and then what we're talking about, right-hand side, you have the information model, some way it comes together in memory. These files, I'm going to be talking about those files. Very, very quick talk. I'm just going to walk through these before we'll go into a lot of detail on those files that we have people actually using. Maybe how can they continue to be used, to be modified, to be used in other ways. We'll also use information. Well, you've already seen a lot of this. Information model, you got all the definitions for the data structures, arrays, and you have the science interpretation of the data, geometry information, as well as the definitions of those terms, the context in which the data is captured, processed, and archived, almost everything. All this was expert knowledge that came from the science discipline knows. We tried to make the point earlier, being written by domain experts, of which almost all of you are. It is the single authoritative source for the data standard. So if you see something in the standard, you should be able to see something, the same thing in the information model. Drives the PDS4 infrastructure by providing shareable, stable information requirements. If you see a requirement in the information model, it's probably a requirement for any tool you're going to develop. The formal definitions, configuring and generating code, structures, but also just text. Basically, let's talk about we're bringing up a help bubble or something like that. The information is also in the information model. And is the implementation agnostic. The list isn't complete. We can go from the information model. We have enough information to probably send any format you could do it right.
Okay, so I'm going to use an example. This is one of the examples I believe that's going to be in the workshop tomorrow. It's just a simple array 2D. These are the attributes, which are being represented here as XML tags. Here you see something called offset, the axes, number of axes in this array 2D image, axis order, index order, some tag that the value must be less index fastest, and then two array axes, 8 and 140. So the question is, what does all this mean? Each model, each one of those terms is defined and with text. All that will be available for anybody who wants to use that in the tools. So now I'll walk through some of the artifacts that are being generated. Most, like I said, a lot of these will be obvious. This is what we call the information model specification. It was the first document we ever tried writing, version of a model that you can click now through. But what this is showing us is that the array 2D image is really in a class hierarchy. Array 2D image is a type of array 2D, which is an extension of array, which is an extension of whitespace, which is an extension of tag digital image object. Come outside, tag digital object is the PDS term that means the same thing as an information object from ONAS. There's no subclasses to array 2D image. It stops there because we don't have to. It does now. There are no attributes, so that's strange, except for the fact that it is inheriting these attributes here from array 2D. The axis index order, description, offset, so on and so forth. The associations or the relationships. Obviously, this is an older slide. This has been deprecated. One of my old slides, so I should fix that. I didn't. Association, which is now deprecated. But you have the inherited associations, again, that are coming from array 2D and array, which are, well, actually, the interesting ones are down below here. Array, the array, element array, and the axes. So we generate the XML schema and the schematron files, which most of you use to create your labels. Information exactly. You have array 2D, which is a type of array 2D image, which is a type of array 2D. And this is the XML schema way to express that. And there's a definition. Definition of array. You can see that it's an extension of byte stream. Definitions, or I'm sorry, the definitions of the elements are offset, axes, so on and so forth. The schematron rule that says anytime you see axis index order, the value in that for that tag better be. So you can see basically how information in the information model was translated to XML schema and schematron. I talked about earlier, both in PDF and HTML formats, you see the same information, just in a slightly different way. Hierarchy here, the attributes, the cardinalities, more information in the dictionary than there is in the specification, and the associations. I'm going to kind of go off into a tangent. This is more for people like Sean Hartman, but what this is saying is that we can create query models. So since all the attributes are defined within the information model, we can specify which attributes would be useful for search, for example. A local dictionary, you say, okay, I want to search on certain attributes. Concept called property maps, which is a part of the information model. Exactly that type of information. Here is we're saying to configure the search service from the information model, or providing a list of attributes to harvest from the product labels. This is attributes and their role, whether in Solar, that was mentioned earlier, a search engine, are they just a search field or are they a passive? Something called collection type. Here we see that it's a field. By the way, there's a constraint called data. This is the query model for any collection that is of mission science data type of attribute. Again, for Sean, basically this information here is telling him how the registry should configure. This is saying there's something called a product observation in the information model, and these are the things you need to extract or harvest out of the configured registry, the harvester needs to extract this information from the label so that he can registry and in the search engines. Now here's the first type of extract that is being used in general for tools. It's the same information. It's a JSON file that you can load into, into JSON. And again, you're seeing array2D image is an internal identifier. That's what looks like inside the information model. But you can see here's the title, array2D image, the registration authority, which we talked about earlier, the namespace, the steward, the version, the description, and then the first association. So this is information that is kept about the class itself. Here is a relationship to an identifier called 2D. What it's doing is saying that array2D image as a parent of array2D association. And this is the basic part of the class hierarchy, which I mentioned earlier. So the tool, LD tool, CLAD, this is the type of information they would be able to use to be able to help build or support, or wizard to be able to support you in the building of your This one's saying that we have an attribute, access index order. And so what you'd expect is that this association, the attribute of array2D image, this is we're associating from array2D image to the attribute if it's allowed. You can see that the other attributes here, which if you're developing software might be useful. The question is, what is access array index order? There's another class within JSON. This is the definition of access index order. You can see all the attributes associated with it, including its title, its namespace, its version, its description, the data type, the min-max values, so on and so forth, almost everything you ever need. And what a lot of people do not know about the model is that even the enumerated values, possible values that are allowed, for this case, access in the folder, they're listed along with the meanings. So every enumerated value also has a value meaning as part of the requirement for developing the information model. So you see now almost every bit of information you'd ever want. If you're developing a tool, then you need to understand the PDS for that development. So that's what's being done so far. We're people actually using this, but we've actually, for our own purposes, creating XMI UML. Basically, XMI is the model that's used for UML modeling, language modeling. In cases like Magic Draw, you can read this and you can be able to draw diagrams. We're saying, and it's basically related through what they call generalization to the array2D, which is the type of array. Put this into something like Magic Draw, it'll draw pictures like this for you. Now, what's interesting here, and I know of at least one person in the group who's done this before, Lucas Bastille, is that once you're in UML, then you can take these UML diagrams and associate code. We can generate by definition the getters and the footers for all the attributes, classes, and understand you can even use it to generate automatically other code, and that's another opportunity for your tool developers. And for those that are into the semantic world, we want to do semantic processing. We also produce RDF OWL. And here you can see that this is where relationships are key. We have the same information about, well, in this case it's array. I didn't do the array to the image. But the array is a type of back stream and x-axis descriptions, not set. This is all in set notation, set theory basically, which basically allows you to create graph databases and the like for more advanced semantic type processing. So people have asked for this and we have generated it for them. We can leverage the IM in many ways. We've shown you how you can leverage it, information in the registry for configuring registry, for the harvester and the search engine. Plaid is using what used to be called OLT, is using the JSON files to help with the processing of that system. And I might mention, see, Bob Dean just got me out from the side. Some work that they've been doing with the imaging node, which is a Vicar and several other 2PDS4 keywords. And that's something in the property map, which I mentioned earlier. And that model, we were talking about how would we make that available to the tools that people are not developing. So that's a thought, and we're starting to think about that. My people at the imaging team, Bob was lead on that. And again, we're seeing how the information model is going to be able to save you from doing manually copying it to your software. You should be able to suck out the information and use it directly. That's the end of the presentation. Oops. Questions?
I just wanted to say that in talking to numerous scientists who are either proposing or have received PDR funding, one of the first things they ask for when they're starting to conceive of their PDS4 archive is that map from PDS3 keywords that they know to PDS4, which is a different language. And so, yeah, making that available, I think, would be very valuable. I mentioned, might have been Sterling earlier, a spreadsheet. I think people who envision doing this, comparing those two, I think have at least envisioned a spreadsheet, if not already developed. So might as well not duplicate that effort.
For the property maps.
All right. Thanks, Steve.
I
We're
just
switching
want to
over.
real quick.
Go ahead.
Just to follow up on that, the biggest thing is that you are producing labels and you do have mapping. So like I know Sterling and I, like we're doing what we're doing in Imaging Node, we're trying to maintain it, but there's no like database somewhere, which probably should be, but like we're building towards that. Sterling wants to do that and we're interested in that. So if you are collecting this information, I presented earlier through that. Yeah, so please let somebody, a node person know, because we really want to get this information.
All right. So our next speaker is Lev, who will be talking about the PDS4 viewer, a standalone display tool for PDS4 data backed by a Python PDS4 read-in API. You did not have the longest title, don't worry.
That title is quite mouthful. So how do I switch to
this display and then PowerPoint?
show from the beginning? It'll actually display it.
I think so. All right.
All right, but wait a minute. I need something more because I need to display an actual live demo. How do I switch the screen to that?
Why not just run duplicate?
So, all right, let me get to that in just a second. Okay, so my name is Lev. I am an employee of the PDS Small Bodies node. I'm going to talk to you about two tools today, which is a tool we developed to inspect PDS4 data, and a Python API to read PDS4 compliant data into Python. And actually, both of these tools are made possible by the formal definitions, which are in the information model that Steve was just discussing. So the PDS4 viewer is a standalone tool. You can download it. It's for Windows 7 and up, for Mac 10.6 and up, and for various Linux flavors. It supports all PDS4 data, so images, spectra, arrays, tables of any kind. And we think it should be useful. You know, it's basically to actually download this tool. You just download it, you run it just by double-clicking on the executable or the app for Mac. For both data providers and for data users. So for data providers, if you do not have a currently in the works, what you can do is open your data with this tool, and at least you have some idea whether you have a gross error in your description of your data structures. For data users, you can use it for basic data analysis, and for more complicated data analysis, you would have to read your data into a programming language. And I'll discuss that at the end of the talk. And for Python, we actually also have a tool for IDL, which I'll briefly mention. Okay, so on to the demo, which I now need to figure out how to actually mirror here. Thank you. There it is. So here I have already downloaded the tool. You double click on the tool to start it. As any tool, you wait a few seconds for it to start up. There it goes. I have some example labels, which I've apparently double clicked on it twice. Apologies. Labels that I'm going to use to demonstrate this tool. So you go to File Open to select your label that describes your data. I'm going to select this one. So a summary window opens, which will tell you the names of all the data structures, their types, some dimensions, and give you buttons to play around with the data. Here, I think there's one array and 6 tables. I'll start off with the data view because usually that's what people are most interested in. So the first part is the image view, and I'll start with a really boring image, but then I'll show you a more exciting image. Image because it lets me show you something that is more difficult on. This is a Spectre image from Maven, I think, and that's why I say it's very boring. Spectre is not usually very exciting images. Well, if this was a non-Spectre image, you couldn't really see anything, so obviously the scaling is off. You have scaling options. You can select, for example, log scale. Now you can see something in your data, which is a good thing. You can select things like color maps. So just so you don't fall asleep, I'll go to a red color map. Options, there's zooming options. You can invert axes. You can rotate the thing. You can add axis labels and things like that. And I mentioned this is a 3D array, so I think this is a spectra. So you can scroll and see that change. And if this was like a 5D array, you could also do that. You would just have more sliders, as long as you describe in your label what was the x and y axis, because no tool can guess that. So that's the really boring image. I'm going to close that, and I'll show you the less boring image, which on this excruciatingly slow computer takes a little bit of time to open. While I was testing. On my personal laptop, which is kind of mid-range, it takes 0.1 second. So I said this laptop is particularly excruciating. And the first thing you get is a warning, and I left that specifically in, even though I could have fixed it to say that it's more than 2D. If you have a 3D array, I need to know what your x and y axes are, because no array can possibly be plotted what x and y is. I can guess for a 4D or 5D array, and I could guess incorrectly for a 4 or 5D array, you really need to specify it, and I'm not going to attempt to guess because I have no idea what x and y is, and no tool can. PS4, there's a particular section for you to specify that if your data can be visualized as an image. Figure 2. This is a bit. I think this is an image of the moon. Let's see. We'll do a more exciting color scheme here. And there you go. You can do something like, for example, I find this particular section interesting. You can zoom in on that. That's imagery. Next, you can visualize arrays as tables, which isn't very exciting. So just skip over that and go directly to visualizing tables as tables, because that's seems more useful. A really simple table. So this table just has three columns. So it has wavelength, reflectance, and uncertainty, and you can scroll down. Data, and if you hover over the column, you'll get whatever is in the label. So, for example, here you know that the units of wavelength are microns. wavelength, you'll get the description for it, etc. It is whatever the data provider put in the label, that's what you'll get here. For tables, so for numeric tables, so one more thing. So in PDS4, it is also possible for a table field to be a vector. So your single value could actually be a vector or even plausibly an array. And I don't generally encourage you to do this unless you have a very good reason. If you have that. So here's a table. Again, this is a Maven data product, and it has just a single record, which I also don't encourage. But in any case, it has an example of this kernels, which is a multi-value field. So if you click the table button, when you get to that, you'll get another table that will show you those values. So I think with numeric tables, or tables where the columns, some of them are numeric, you want to plot them because it's not super useful looking at a giant numbers. So for that, there's plot view. You click the plot button, you select the columns. In this case, it's really kind of table with 3 columns. So there's an X and uncertainty. So you can have uncertainties that will also be plotted. You can make it a line plot. You can make it a scatter plot. I'll leave it as a line plot in this case. And so then it opens up. I'm going to fit it to actually fit the window size. I'm going to adjust axis to fit the whole screen. Other adjustments you can have, so you can invert things, you can scale things log or some other type of log, X log, Y log, etc. You can change colors, you can change labels, etc. I think I'll change here is I will just a little. People can see it in the back better. And then I'll change the line color to be gray, for example. So there you go. You apply it, and there's a plot. Okay, so that's plot view. And the final feature of this tool is and again, I'll open the more interesting labels for each particular thing. So for this label, you want to look at a label. So, XML is kind of human readable, but it could be a little bit better. So I devised this little view where you can scroll down and see your view, and what people have told me is more convenient, although less than certain, but a lot of people have told me that this is convenient, and you can do searches on it. So you can search, for example, for target, and you'll get the target of this label is multiple. It's an assembly of commentary nuclei data from many comments. So that's label view. So that's the tool. That's PDS4 viewer and demo. And as I said, this works on all the common platforms. Windows. I'll go back to my presentation. Okay, good. So we're done. We're past the demo. Now the Python API. So okay, you're a serious scientist. You want to read the data into programming language. You're maybe familiar with Python. Maybe you want to get familiar with Python. I don't know. But itself is backed by this API, and this API is separately available. You can actually also run the viewer from Python if you really wanted to. The Python API to read your PDS4 data is written with both scientists and software developers in mind. So it basically tries to keep things simple, where I think scientists will be using it, and more complicated, more advanced features for software developers. It supports all PDS4 observational data with one exception. And it provides access to both data and label metadata. So for example, if you wanted something from a mission dictionary, like you wanted to know what's the filter name for this image, you could easily pull that. It is compatible with both Python 2.6 and above, so including 2.7 and Python 3.3 and above. So we tried to make it have a rather wide range. Dependency NumPy, which is if you're doing any kind of data analysis and you're familiar with Python, then NumPy is basically a requirement. Cross-platform, so anywhere where NumPy and Python can be compiled, this tool will work because it's written entirely in Python. The thing is, I have a talk at 3:30 in the other room, which will go a little bit into a little bit more detail. So if you, for example, have particular data that you want to read, and you want to see exactly how you do that, I mean, the spoiler is that there is a manual and it's simple, but if you want to come and see that, you can. Go into a little bit more detail of the API today. And here are the download links if you want to play around now. If you just search PDS4 Viewer in Google, it'll come up. And the last thing is that we do have a tool for IDL, which it's a little bit less polished, but it has a very similar purpose. That it's actually available at that second link of PDS4 Reader. That'll link you both to the IDL and Python tool. And that's all I have. Thank you.
Just as a memory footprint, are you allowed to load in for tile, for band, for?
Right. So I guess the question is for arrays. For arrays, there is an option to read sections of arrays where you select which particular section you want to read. So you give the ulysses. And essentially that uses memory mapping. So it'll only load eventually the section that you actually select.
Okay, perfect. I worry when I see a standalone viewer when we're trying to load, a 40 gig image.
So for viewers, that capability is not available. So for a viewer, you'd not be able to view a 40 gig image. For the read-in, that's what I'm talking about. So the tool of, I just want to read a particular piece of my insanely large mosaic.
I like this. I think a lot of people are going to use it when they know about it. Is it on GitHub and can I contribute to its development?
I've been asked a fair amount now. So it's going to be on GitHub by the end of the week.
Okay.
Okay, great. Thank you, everybody.
You stole the mic. I hate that guy, Trent. Who does that Trent guy think he is?
Okay, so our next talk is from Rishi Verma, and Rishi will be talking about next generation parallelization systems for PDS image node assets.
Hi everyone, yep, my name is Rishi. I'm at Jet Propulsion Laboratory, and today I'm going to be talking to you in this presentation about some data challenges that we're facing in PDS imaging node, and some software technology that we're developing to help address those challenges. Let me start with the challenges. So one of the major challenges has to do with data, because we have a lot of it. We have around 650 million files, roughly around 65 terabytes plus of data, not including high-res images, which would probably push that number well over 100 terabytes or more. And so that presents some challenges, as many of you are probably aware of in other nodes as well. One of those is integrity of the data, or just making sure that that matches what we think the specification should be. So, for example, we want to know, years after publication, the place where we stored the data to our archive are all the links, the file names, the integrity of the data is exactly the same as what we originally thought was the case. So that's a challenge when you have that much data. Another is we might want to augment the metadata, add in additional that we think is useful to our customers for our own internal purposes. Doing that on a subset of data is not that difficult, but again, when you have this many files, reprocessing or extracting metadata can be challenging. So that's really the challenge that we're looking at. And to address that, we've been working on this piece of software called the Archive Inventory Management System. And that's the subject at the top. So, main objectives, and it's to address those challenges that I mentioned. So, one is we want to validate that assets that we have stored in the PDS imaging node have the right characteristics. Archive, you'll come across this sort of cases, but we want to check things like file size, checksums, permissions, link integrity. Is the data duplicated in certain cases? We want to check all that on a continual basis. We also want to, again, I mentioned, be able to augment our metadata. So what we want to do is, since we want to look through all of our data assets and be able to assess its validity, integrity, in some sense, we want to make a platform such that we can do other operations while we look and scan this data. The objective of AIM is to offer a platform to more efficiently reprocess and add metadata to all the files. So, so the real core of this, the algorithm you could say, is really just the extraction part, which is not terribly complex. We just want to extract information. Right now, we're looking at things like file path sizes, instrument mission, typical files. We also want to take in snippets, like text snippets, and text files, so that we can, down the line, do more sophisticated text analysis of the files that we have and match certain characteristics of questions. So that's really what we want to do at a very core algorithmic level. Once we collect that metadata, or augment that metadata questions. So I'm going to take that metadata, put it into a metadata search engine like Apache Solr or Elasticsearch, and be able to ask questions to it. Things like, data is duplicated. Are we taking up extra space that we don't need to? The data that we're advertising on one of our core or customer-facing is any of the data that we have in our archive not advertised there. So is some of our data hidden that we don't want to be in? Which files no longer exist, which are corrupted? And we can also do some interesting analytics to see which missions data characteristically over time and how does that fluctuate. So there's sort of a data analytics as well as answer sort of use case here with respect to AIM. And again, any archive from this type of these types of questions or answers to these types of questions. So that's sort of the objective and what we want to do with the metadata once we collect it. Now I want to talk a little bit more about how we're going to do that. We've got the challenge, we've got the metadata we want to extract. But again, I mentioned the big challenge was the volume of the data. So we've looked at a couple different strategies, and in a very simple sort of outline, we're looking at a couple different strategies, right? One is sequential processing, which at a very basic level, if you look at one image file, you extract metadata, you look at a second image file, and a third image file. And in many cases, like thumbnail generation, for example, that we do for our image assets, that's the way we do it right now. And we choose sort of a subset of our data, and that can, it takes a couple weeks to generate the thumbnails total, but you can imagine for 650 million files, say it took 1 second per file, who's good at math here? 650 million files at 1 second, that's it's about 20 years, right? So that's a long time on a single computer. So obviously this is one of those tasks where if you do it in parallel, you'll get a lot of benefit. Couple ways to do that. One is to leverage multiple cores, and that helps definitely. So you give different specific metadata that's being extracted to different CPU cores, and that can reduce the time to this kind of extraction process for all these files. Another way is you imagine you have the same files and you just do them all in parallel at the same time. So of course this depends on how many computers you have. only a few computers, then you won't really get as much data as you want. That line of thinking talks specifically about the multi-server approach a little bit more architecturally, since it's the most interesting. So in that line of thinking, what we decided is that we would investigate and try out renting web services. So actually not specifically renting servers, just processors. So there's a tool that came out, I think, 2 years ago from Amazon Web Services called Amazon Lambda, which lets you just rent processor CPU cycles on demand if you need them. You don't load any servers. So you just sort of give your algorithm and it runs your algorithm against data that's sent in. So that has some benefits, especially related to continuous scaling, up to 1,000 or more potential concurrent processes running on demand. And then you're also built only for the execution cycles that you use, so time and set downtime, etc. That's sort of the approach we use. I wanted to give a little bit of architecture for those of you who might be interested. So how this would work and how we're trying this out is that we have our archive, and what we do is we would send our files over to Amazon Web Services, which is their storage system, automatically trigger our metadata extraction process or thumbnail generation or whatever algorithm we have. We do it on demand in parallel as we're uploading more and more files. So this is just trigger new processes, new containers actually. They're using a containerized approach. We would collect the metadata, we would store it in a metadata search engine, like I mentioned, Solr or Elasticsearch, and then we would actually just delete the file immediately. As soon as after we finish the processing, delete the file so that we don't incur. After this whole cycle of uploading, processing, deletion finishes for all the files, and we replicate our metadata store, which is a very, very small subset of our entire data, and then finally just delete the data from Amazon. So basically, there's a clean slate after we finish processing. Our server costs are zero after that. So it's sort of like a burst model, you could say. Just people are always interested in this. Okay, how much does this cost? And we were definitely interested in that. So it change depending on what Amazon decides. But right now, what we're looking at is that there's a free tier of about 1 million requests free per month. So a request is like a trigger. Whenever you upload a file to process it, and then they also give about 260,000 free at a particular charge. So we go way beyond that. So we're really more in the additional cost section. And roughly speaking, that total will come into about the entire archive to be burst process, not including the amount of cost to download the metadata after we're done. Okay, so I just wanted to quickly just mention an experiment that we did with respect to this approach. We took a messenger data set of about 74 gigabytes in size. Each file is actually very large, so it's a little bit of a different type of archive or data set. What we want to do is run the extraction process and see how well these different methods perform. So this is actually pretty interesting because we got some unexpected results, and that's because you don't want life to be too predictable. So we found out that it's about 14 minutes to sequentially process these files on our server. About a little over 10 minutes to use the multi-core approach. Actually took 12 minutes for this Amazon Lambda approach. So what happened here? This was supposed to be a lot faster. It was a lot faster. It took about a minute to process, but it took 10 minutes to actually just send the files. So I had a prediction that this would, but turns out there's a lot of transfer costs. That is an issue because even at 100 gigabits per second, or terabytes worth of data can take a long time to upload. Can we do better though? So some of our next steps thinking about this is Well, we could try some other approaches like parallelized uploads, and that actually obviously divides our upload costs strictly in half. So it's actually more expensive to process than it is to transfer. This might help us. Amazon has a couple of approaches to reduce the cost for uploading as well. Amazon Snowball and some other just. So actually, it turns out that this would take about a week on average to send over the entire archive. The LCs and computers while we're using it, but even that it scales better than the multi-core approach because 12 cores on our computer. But we can scale up to maybe 1,000 servers. So our parallelization for millions of files will over time be better than the multi-core approach. If we spend money for it. Stage we're at, we're still sort of evaluating what the best approach is, and that's about it. Yeah. So any questions, comments? Thank you.
PDS. So how often do you envision running this process? Say if it became production way of integrity checks for the node.
Yeah, so I think it's rare. It's rare, obviously. So I think the initial bunch would be once we would have to run it for every file that we have just to have it done once. And then typically after that it would be on change for the new files that we ingest. We want to make sure that they're run. I think the exact timing of how often we want to run it depends on the cost model. How expensive will it be for us to run? Because ideally, if it's not that expensive to run this kind of process, it's every time that there's the data archive, we can validate that the change didn't affect any other kind of files. So we're still kind of figuring out the exact timing about that, but probably it'll be a little bit more on when we get a large kind of change in the system that will run this.
And do you have a strategy for hiding from JPL the fact you're going to use 100 megabits per second for 7 days?
Yeah, I'm figuring that one out too.
Right, thanks, Rishi.
Okay, well, this is coming up. I'll interact that. We're talking about one of my favorite topics, which is automated content detection for Cassini images. And she has the notable talks before and after the break.
So good afternoon, everyone. I know I'm the last talk before the break. I'm also the first talk after the break. So you get me twice, but you do get to get some treats in between. That I'm at JPL in the Machine Learning and Instrument Autonomy group there. And I'm going to show you two different interesting machine learning projects that we're working on. I work with Alice Stamboli, Brian View, and Alphon Altanok. And Alice is here as well. Hi, Alice. And did the bulk of the work for this actual project. So please, if you do have questions, she's definitely an expert, and I think she'd be happy to take your questions as well. Doing this work is to enable content detection within images at the PDS imaging node. Okay, so Jordan already gave you a preview of this earlier today, how this is a new capability that's being provided by the Planetary Image Atlas. Some more information about how this actually works under the hood. I think this, one of these is the laser. There we go. Okay, so here you are on the Planetary Image Atlas, and Jordan showed how you can type into this unified search box. And initially what this allowed you to do is type in any content, the metadata for any of the images there. So it would allow you to search on anything that defines where an instrument is being pointed. What are we looking at? or where, or how, or by what instrument. Having the capability also to search on what ended up being in the observation after the fact. Actually see, not what did you expect to see only. Note here with, PDS has a lot of images in it, and Cassini alone has, this is just the number of EDRs within the archive, is also very large, and this motivates the ability to search for images that contain things you personally care about. So in order to do this for planetary images, we first look at the Earth for ideas on how to proceed, and the ability to search for images with it's a big business on the Earth. You can probably come up with your own examples, but just think Facebook, Flickr, anything that relates to finding images that relate to a particular concept, and specifically concepts that can be described in text. Heavily invested in on the Earth. This is just one example from a system that was developed at MIT where you have lots of these beautiful Earth images that have been described by interesting and rather complex, in some cases, concepts that you can now search on and get images that match. To do this, we're going to borrow from those lessons learned with Earth-based data, and image classification by content would be the convolutional neural network. Heard of a neural network before? I'm actually curious. Okay, why do people? How about a convolutional neural network? Okay, who's used a convolutional neural network before? All right, so some people have. Excellent. I'm not going to go into the nitty-gritty details in this very short, 12-minute talk, but I want to give you a shallow introduction to deep learning here. This neural network, these are often referred to as deep learning because you won't be able to see the details here, but there's many, 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 many layers that are stacked up that your image is going to flow through to actual concepts that's at the output side. Convolutional is just a word, but all you need to know is that it encodes something very special that we know about image data, which is that there is high spatial correlation within an image. Those are not independent samples, but in fact they are strongly correlated, and the convolutional neural network leverages that to do better classification of image data. Another nice thing about this technique is that it gives you a posterior probability for every prediction it makes, proxying for confidence. So you can actually see when the system is giving you a very confident judgment or one that it's not very sure about. The ability to do transfer learning. You may have heard, if you know something about deep learning, that these systems require not only often millions of labeled examples to train on, but lots and lots of time to process all of that data, because there are thousands or hundreds of thousands of free parameters within a given network that have to be optimized. But instead of starting from scratch on your new problem you want to classify, train network and adapt it to your problem where it's already figured out all the low-level details, and then you need fewer labeled examples to train it on and much less training time. So this is a huge benefit of using a system like this. Once you have it trained, you then have, well, actually, this is the training process. You've got some images, labels for each one. That through the deep learning system, again, this can take hours, days, weeks, depending. Out that you can then propagate it through the network, and you get out predictions for the closest match to things that it has been trained on. And in a little more detail, then, this gives you a sense of how those layers conceptually work. On the left side, you take in just an image with individuals. And as it flows through these layers, it's abstracting further and further away from pixels features that progress up to things like edges, textures, objects, and ultimately to entire objects. Showing, for images of faces, but you can imagine the same thing applying for parts of, in our case, planetary bodies and other features like rings. So what you see here is that this beautiful resource that is out there in the community. This is a pre-trained network called ImageNet. It's been trained on images of Earth scenes specifically, but they're of immense diversity, 22,000 different categories ranging from bicycles to flamingos to beach scenes, just about anything you could think of. 15 million images went into training the system, GPU to train. But then they put it out there as a community resource that you can use if you have, say, your own favorite images from your family vacation. You can classify them with this existing resource. You can try to adapt it to some new problem, which is what we'll do in this system. So how does this work? This pre-trained Earth ImageNet, if I give it, in this case, an example image from MSL, this is a selfie that the Mars Science Laboratory rover took of itself. And so there's a demo, you can go here if you want, that allows you to just upload your own image and just see what it does. So this image, the best matches it could come up with were aquatic bird, wading bird, stork, which is clearly wrong. I think everyone in the room, even those far in the back, can probably tell that's not. But if you've never seen the Mars rover before, and if you've never seen Mars, if you kind of squint, it does look a little bit like a gangly, I can see that. You know, closest matches, but it highlights the limitations of the system. It doesn't know anything about planetary data. And here's a Cassini example of a jet or plume, I think. I'm not actually sure exactly which image this is, but again, it's best guess spider web, trap, invertebrate, you know, way off, but not crazy. These are not implausible guesses if you've never seen this kind of image before. Let's take that existing ImageNet and adapt it for Cassini data. So we refined this classifier by using a system called Café, which is open source, available to anybody. You can download it, you can try it out yourself as well. You give it your own image data with your own labels in different categories that were relevant to Cassini image data. You adapt that trained network to work with those new categories. In this case, only taking about 10,000 images and then a few hours on the GPU to train. The vocabulary that we used for the categories of interest on Cassini, really a kind of a proof of concept. So we identified some interesting categories with no effort really invested in, are these the most scientifically relevant and important categories? This is really just to show that this fine training process could work from the Earth data to the planetary image data set. So this is not the final set of categories that we will be providing, and we are actually interested in any suggestions that you may have as well. But right now, they're pretty much broken down into kind of more actual physical content of the image, considerations like, you know, are there multiple objects, how far away from the camera the objects are, and then a whole host of sort of artifacts or noise categories. We don't necessarily care that much about finding these things, more that we want to be able to filter them out. So if you can identify them, you could provide the ability to suppress them in search results as well. So this is the kind of output that you get for 5 sample images. And 2 of the 19 categories, you can see that I'm depicting this visually. For the crater class, this is like 100% no craters in this image, 100% no here. 80% yes, and 20% no. It's a real value posterior that allows you to, if you like, threshold on that confidence and only look at the results that meet a desired performance level. For this class, it has a different response function to these same images. And these classes they can be overlapping. So within one image, you may have multiple relevant labels that the classifier is predicting. You could have a star field and craters and rings and so on within the same image. Here's some examples that have come out of the system. For example, these are images that were predicted as containing rings, and they do indeed seem to have rings, which is great, even though they are quite diverse. And again, if you know nothing about images, it might be hard to connect these to being the same kind of phenomenon. The training process has informed the system of that. Here's some Other examples from the crater class that also highlight a lot of diversity. You can see that they're very different and how much that the object is filling the scene and all that. And this one, I'm not entirely sure whether these truly are craters or these are some other potential artifacts. But if you were interested in craters, these are exactly the images you would want to come up so you could investigate more deeply and determine if they would contribute to whatever your study objectives are. So you can try this yourself today. You can go to the Planetary Image Atlas. Here's that same menu that Jordan showed briefly. You could click a category. I click something like this. One caveat is that you will see a bunch of results. And unlike, say, Google image search or other Google searches, they're not ranked by relevance. That may be your first instinct, because they're ranked by relevance, right? No, I believe they're actually ranked by image acquisition date. Don't want to correct me. Something like that. Or product ID. But they're not shown here, but if you scroll to the top, there is a tiny place where you can specify what that source should be. And if you click on that and go to Cassini confidence, by descending or ascending confidence, depending on what you want, and you may actually see better results that way. So give you that tip if you want to play with it. So in summary, our goal here was to use state-of-the-art image classification methods to enable content-based search for images in the PDS. And this can really transform how we interact with mission archives. You're no longer restricted to getting results that match observations and pointings, but now you can discover observations that maybe were serendipitously included. Maybe the target was a specific moon of Saturn, but rings were captured within the field of view too, and you wouldn't have known to look there unless you could search by the content. We're interested in expanding this to other image categories. I have an example here from Rob French, thank you already, for these propeller features within the rings. A great one. Still an area of open research in the field, and we'd like to be able to find and capture all of these things in the images. We've also developed similar systems for MSL body parts. If you'd like to go and look at this, it's a different drop-down on that same menu. And also high-rise features like craters and dark slope streaks are another selection that you can explore. So thanks very much.
Maybe take two and then we'll take a break.
I had a question, actually just two quick questions. One was when you're running this on very large files, like say it's, the image file is 10 gigabytes or more or something like that, is there sort of, does it take a lot of time to process or is it very quick? And the second question was when you had mentioned you use Cafe and sort of extended the existing sort of image classification system. So I was just wondering whether it's you have any plans to sort of redistribute this back to the original kind of archive to make sure that it builds up on.
Question. So I think Alice could speak more to the scalability point, but I don't really envision this working for gigabyte scale images. It does still have to process all the pixels in the image, and you might be able to find the features you care about even with the reduced form of that gigabyte scale image, or chop it into pieces if that's what you really want to do. But if you did it for the full image, you would get like one yes or no for each class for the entire image. It's useful to zero in on specific areas. As for contributing the now trained Cassini model back to the community, excellent idea. Sort of model zoo that people can contribute to, and that others could then access that model and build on it, refine it further, and so on. So great idea.
Hi, I'm Michael Ayer. Just to reiterate if I understood it correctly, you used the 15 million 22,000 category trained machine learning network, and then you put the 10,000 Cassini images, and it wasn't 100% clear. Were they labeled or not? They were not labeled, right?
The 10,000 Cassini images were hand labeled, yes.
They were hand labeled,
yes.
so then I don't understand what we got out of it. If we you already got the labels?
Oh, well, we then processed the, 500,000 Cathene images.
Oh, sorry, okay.
Yeah, yeah, so we still wanted to expand to the full set.
So then the training, with the training to Karen, yeah. So I was wondering if it has to be categories already existing, obviously, in the
Yes.
training phase, right?
Yes, it will not discover new categories for you. However, if you run it and all of your existing categories no or low probability, it would be a clue that you might have discovered something new.
Okay, thanks.
Okay, thank you, Kieran. We're on break until about 3:15.
So on the metadata that I see, how the navigation process happens. Unless you want to do it right, exactly. But what I'm doing now
And there's but I don't know if this is connection.
Okay, sorry. Got it. Because we
did something kind of similar.
right. So what I don't even know if it's happened.
We're using,
So, would you use like data parking lots?
yeah, it's got all the parking lots.
But you have cores, on the other side, probably
Yeah. Yeah, so, yeah, I'd be curious. All right. Yes, what do you think? Yeah, I'll shoot you. Yes, actually. Actually, I have no idea.
I do have black bodies. You do? Okay, sure. So you basically use the geometry. Yes. Yes. Yeah. Okay, and it's just out fast. Right, but if you want me to do some talks in the current catalog, I don't.
And you know, that would be great. I don't know.
Well, okay, so actually, okay, so the start catalog, the start catalog already get, you can start, okay. The start- And, yeah. Some of the points, yeah. We don't do that. That's pretty easy to have. Price, which is very quick. Okay, this will use our starting on a place. That's the real thing. Wind up. I just did it, that's why. It's the point. Why is it that sometimes? He wanted like whatever I was doing to make something she'll want. Follow. So classification, so it's cool, a lot of geology. We have a yes, no program. Okay, so let's bridge. So you actually get. All right. Was he happy on? So, yeah. Oh, okay. You are great. Yeah. I mean, I'd love to have some. Okay. It's me right now. I think I have to do this. Yeah. Where there's a star that failed to cross the right, you would actually like the flare rate energy would be hard to get, but the flare rate. The way that this image is that, of course, a lot of stars yeah. And so depending on where that there are zero stars, the large fractions. There are experiments calibration or where they data when they see the energy and low exposure works. And those are the ones that are actually useful. The exposure time, and a lot of that has to be range. Yeah. And if you remember that like a plot because your was seen basically. So and of course, But on stars, which you see stars on the you see stars in a lot of it. TV comes more or less along the line of plane. Right, so in fact, if you look at the graph, there was a secret code in the graph that I thought it was explained. See how these all three have just some of them, and some of them have circles. Right? All the ones with the stars, they have to be doing stars. Okay? These were two images that for whatever reason I put one on the stars and stars, and I had to use the edge of some of these parts of things, for example. So you can actually look during these three images and say, oh, here's a whole bunch of stars. Now, it is true that the orbit, the stars are shifting. So it's not like you get the same stars that are fully you get, maybe you see a star for 2 or 3 images. You get time resolution minutes.
It's the same star 3 times.
Right. So, it's going to be a low probability, but you might be good. Yeah.
It's one of our systems. So we started with four, then for one we have now 10 systems. Here where you have to change this file. Sometimes that's exactly most of the development or new locations where
Right, I had this problem all week. Yeah, as well, at some level, actually, tomorrow. It probably works better. Because I don't have any other conflicts, staff open.
Okay, everybody, we're going to come back from our break here. Surprise, surprise. Yes. So here she goes. Sorry. Mars Targeted Encyclopedia Information Extraction for Planetary Science.
All right, everybody, welcome back from your break. Again, I'm Carrie Weisstaff, and I'm going to be talking to you about something entirely different. Analysis of planetary data. This is the analysis of text planetary data. So it should be pretty interesting. This is joint work with Raymond Francis, Dami Gowda, Stephen Liu, Ellen Ryloff, and Karanjit Singh. And in the nutshell, introduction here is that we're taking techniques that have been developed in the medical literature field from text and make it available in a searchable format. And I want to do that first. So our rovers that have been exploring the surface of Mars now for quite a long time drive around on the surface, and as they go, the human operators identify interesting targets, which might be rocks, they might be layers, they might be drill sites, and so on. And they give them these names, like you can see here, Sheepbed, John Klein, Cumberland. These names have no semantic meaning about the target. They're often chosen to reflect Earth locations or people that have nothing to do with this target. It's just a convenient descriptor that tells you that something interesting was there. And we're going to, for this purposes of this talk, zoom in on one particular instrument on the MSL rover, which is the ChemCam laser, the LIBS instrument, which allows us to shoot a laser from the rover to a remote target and get a compositional spectrum out of it. So this is really cool. From here, there's a way I can shoot my laser and figure out what everything is made of in terms of the actual atoms and elements that are present there. So for every target, and ChemCam has now collected hundreds of thousands of spectra for these targets on Mars, you can analyze those and find out interesting compositional information. Easily searchable repository of that information. You simply can't ask questions like these. What targets on Mars contain fluorine? Now, you could download all the data and process it yourself and arrive at an answer, but there's no way to just ask that question and get a result. You certainly can't ask which targets contain a mineral, like plagioclase. And you definitely can't ask if there's consensus about how to interpret a given target's composition. These are interesting questions that not only you might be wondering as a researcher, but can drive new scientific investigations of Mars. So I'm going to borrow a concept that was in Ross Byers' talk yesterday, this beautiful pyramid going from data up to wisdom, to give a sense of what we're trying to accomplish in this project. So for ChemCam, you can start with the actual data, which is a spectrum. From that, you can derive interesting things like oxide compositions. And both of these levels of information, the data and the derived information, are available on the PDFs for anyone who wants to download and use them. Higher level, which you can think of as knowledge, which is what the scientific community has learned from that data. And that is what's been published in the literature. Information that has been digested through human brains and turned into knowledge. It's out there that we could be using. If you want to be able to answer these high-level questions about these targets, and then of course there's the highest level of information, which would be wisdom, which is something like our collective understanding of what's happening currently and in the past on Mars. We're going to be quite up there, but we're going to be at this level, extracting information from the derived product. So the way we're going to do that is build something called the Mars Target Encyclopedia. So ideally, this has an entry for every target on the surface that collects all that's known about this target and allows you to access it. To do this, to pull information from scientific publications, we're going to use automated information extraction, which roughly is broken down into two phases. You analyze all of the text and look for interesting entities. Our targets on Mars, they're elements and minerals in this case. So we started pretty simply. And then secondly, you do relation extraction to identify what are the relationships that are stated in the text between a surface target and its composition. Extract from those two phases goes into this database, and then you can search it. So let's begin with how you would do this manually. This is an excerpt from an abstract at the Lunar and Planetary Science Conference in 2016 by Johnson et al. This is two sentences. A web-based text annotation tool to annotate this document to highlight the knowledge that's captured within it. So you have a target called buckskin. It contains a mineral magnetite. It also contains hematite. It contains iron, an element, and so on. And you can see that the way people write these abstracts, nobody really writes target X contains Y, period. One would be trivial, right? They would simply mine that useful list of statements and we'd be done. Instead, people say things like, likely owing to the presence of, and with minor phases. So it's been said before, and it's certainly true, that humans are infinitely creative in how they compose the written word. And we need a system that can be adapted to that, which is why we've turned to machine learning to help us a whole bunch of existing text and tell us how to extract that information, even if we can't predict exactly how people are going to talk about these things. So once you've manually annotated, say, 100 documents, and then we built a web interface that allows you to search it. So you can type in your favorite target name. Here I've typed in Dillinger, which is a target. And it tells me that there are 7 properties known in the documents that were annotated here. And 3 of those 100 had information about Dillinger and its composition. So you can dig in and see what those properties are. Here we learned that Dillinger contains fluorine, it contains potassium, and if you scroll down, you'll see the other 5 things that it contains. But what's interesting is it doesn't just assert that it contains those things. Evidence. For each one of these, you have an actual sentence that this shows you Dillinger contains fluorine. The excerpt from the source document, you get the full citation, and if you click on that blue link, you get the PDF of the source document, and you can see the full context, not just a single sentence. So you get attributed claims about the composition of this from the literature. You can also enable other completely new kinds of searches that aren't currently possible. Here I've typed in a mineral, hematite, and it says there are 9 different targets in the database that contain hematite. And thanks to Fred Califf, plot on the rover's spatial traverse in red are all the dots where there's a target that the scientific publications say contains hematite. So you can start to see how it's distributed spatially on Mars as well. So how does this actually work? If I go into those 2 phases, starting with the named entity recognition, task in natural language processing, but this is one of the very first times I think it's going to apply to planetary science literature. So here we use a standard package called Core NLP, developed at Stanford, including systems to find and classify all entities within your document. And this is a generic tool, so it comes encoded with the ability to find people, locations, organizations, etc. But you can define your own entities, which is exactly what we had to do for this task. So we define elements, minerals, and targets as being entities of interest here. System on the annotated document. We trained it actually on documents from Lunar Planetary Science Conference 2015, about 60 documents. and tested it on about 50 documents from the next year of LPSC. The hardest ways to do it, I will say, because in 2015, there were a certain number of targets that had been identified by the mission. 2016, new discoveries had happened, new targets had been identified, named, and studied. So just by learning about what's talked about in 2015, you're always going to be at a disadvantage. So you really have to be able to generalize to do a good job here. Performance for the three classes, element, mineral, target, and overall. And in green, you're seeing how the machine learning system performed. A non-machine learning system that we developed, which consists of a system that consults lists of known elements, minerals, targets, a bunch of heuristics to avoid spurious detections. For example, initially the system likes to detect people's middle initials as elements. So everyone who had a middle initial of C was carbon, and everyone with B was boron, and so on. So we had to hand code a lot of hacks to get around that. The machine learning system didn't require any of that. Element and mineral classes, pretty much the same performance, pretty high, above 90%. And it's the target class that's the hardest one. Targets are discovered every year. Generalized, especially when there's no pattern at all in the naming conventions. They are pulled from, as I said, Earth locations and people, somewhat arbitrarily, sometimes themed, sometimes reused from old missions like Viking, unfortunately. And so there's a lot of, this is a hugely challenging process to automate. But good enough for deployment. So we move on to the next step. Finding the basis between the targets and the elements and minerals. Using a different system that's trained specifically for that task called JSRE. That's given a sentence, and you've already found the target, you've already found the minerals, etc. For each such pair, it tries to predict whether or not they are related. Whether this sentence is saying that Confidence Hills contains plagioclase or contains augite or hematite. Say that. But it has to be able to learn that from the data. It's a lot harder than simply just finding the STs. But here's how it performs. Again, I'm using green to indicate our machine learning system's performance and orange to use a non-learning system, which simply says if the target and element or mineral are in the same sentence, it just makes that blanket assumption. It is often the case, especially if there's only one target mentioned in the sentence. All the way there, and the learning system is improving over that, although you can see we have a ways to go to get to perfect or human level performance. We were able to run this on documents from LPSC and extract useful information. So here is a characterization of the the manually annotated documents, 118 of them, and all of their contents that were manually annotated. And then I turned this loose on everything from LPSC 2014, 15, and 16 to see how it would do, which is almost 6,000 documents. Found a lot of stuff, a lot more stuff. Orders of magnitude here. In terms of the targets, not as many as are probably present, because as we saw, the performance for that was lower. And with the relations, expect. Now, not every LPSC document is talking about surface targets on Mars, so we're not really expecting this to scale precisely. These documents were specifically chosen because they were about ChemCam. So a lot of these are not relevant. However, it is pulling on useful information, and it takes us about half an hour to process one document by hand and only 5 seconds for the automated system. So it's able to churn through lots of text very quickly and pull out interesting information. This is just a characterization of which targets were being found each year, and if you stare at this, you can see how it evolves over time. But I don't have a lot of time left, so I'm going to quickly go to what we've done in this project, which is to connect data to knowledge that's already been published out there, and which can be a rich source of complementary information about these targets, especially highlighting being publication worthy. So you're getting the best of the best. The findings that were considered interesting by the scientists involved that were considered extremely important, and you're able now to search this. Our next steps are to integrate this. Tom gave a very good talk earlier about the analyst notebook and how we're going to integrate this so that you can not only look at the target, but you can click and see its publication history. Where has it appeared? What do we know about this target? Something you couldn't do previously. On to integrate journal articles, which are much longer, more complex than LPSC abstracts, but are peer-reviewed, which will give them an extra level of reliability in the databases. To take your questions.
So I found it interesting how the mineral identifier was the best result in machine learning. Is that simply because mineral identifiers are so specific with specific? And if so, what's the 5% that they didn't identify? Is that the shortest mineral name? So if you split up that plot by length of identifier, then it's best for the longest?
I don't have a full characterization of exactly which ones it was missing, and there are two systems there. There's one which is the non-machine learning, and honestly, what that does is look for things that end in ITE. What minerals do, but not gypsum, for example, right? And then the machine learning one is looking for how they're used in sentences. A given mineral has never appeared in any other context. If it has not appeared in a known context, it will be hard to find. But if you talk about it in similar ways, even if it's an entirely new name that doesn't end in ITE, then it gets it right.
Okay, our next speaker is Diane Owens. Interactive machine learning for discovering patterns in spectral data and imaging.
Right, thanks. I am actually a machine learning researcher at the National Laboratory, so of course I'm pretty sure that if you give me a few grad students, we can solve this whole planetary science problem in a few weeks. We'll see. So honestly though, for doing machine learning for scientific discovery, I didn't use the pyramid that I've seen a few times this week, but this is a diagram that I came up with. The whole flow starts with, we do a lot of sensing, right? To produce digital data, which is pretty much what we're working with these days. And the signal exploitation is something that I work on science questions. Yeah, there we go. Of course, is we do signal exploitation in some way. We transform that data, analysts end up looking at that information, try to make discoveries from it. I think the way that we can incorporate more machine learning is not actually to do, we'll give you the answers. But somewhere in here, we can make this process faster. We pull out of our data and how it's interpreted, machine learning can contribute. So the goal would be then to accelerate the speed with which scientists can explore the answers to their questions. So nobody has mentioned machine learning to you yet. I'll tell you how I think of machine learning. It's function approximation. So we have data, which I usually call X, and typically in machine learning we also have labels Y, which can be any kind of a label, really. But is the more X's and the more Y's you give the learning algorithm, the better we can get at figuring out what this mapping is. This is the function approximation right here. What's the mapping from X to get to a Y? And the form of that function are all those buzzwords that you usually hear: support vector machines and neural networks. Another way to do machine learning, which I actually work on more often, is when we don't have Ys. We're not really sure what the labels are, or we just haven't had people to label them yet. And in that case, a function approximation or a probability density estimation. The question is, where is all this data coming from? Can we come up with a probability distribution that this data, basically? And those go under the names of clustering. Probabilistic graphical models is my favorite method. And again, the X can be pretty much anything. And so in this talk, I'm going to give you an example of one thing I've done with ChemCam data. I'm going to talk about some work that I've done on non-planetary data. But for the reason of having you think about what are the sorts of problems that we can fit into this model, it might not be, is there water on Mars? That's not the question we're trying to answer. We're trying to figure out what sorts of data can we put into a machine learning algorithm to help an analyst find the answers faster. So the first example I'll talk about is using machine learning to discover patterns in ChemCam spectral data. So fortunately, Kiri mentioned ChemCam a little bit already, but I'll talk about it again. ChemCam spectroscopy is a spot spectrum. It's a little bit more than just a regular one spot because you fire the laser and collect more spectra. You actually get a depth profile into the surface of rocks or what I'm usually looking at. And one difficulty is figuring out what the actual elements are that are present there. We can sort of get a qualitative answer, but it's very difficult to get an absolute abundance of elements. The way we usually want to ask these questions is what sort of elements are in there. So I've looked at this problem from a different perspective, which is to first look for relationships among the shots to see how the elements are changing without even really knowing which elements are present. I'll show you that example. But the reason to do it that way is because some of the questions that Nina, who's a co-author on this, are looking for these surface coatings. Other people are interested in veins and stratigraphic layers. Okay, so to get at the types of questions that scientists are asking, I'm going to look at how does the spectral response change as we sequence the shots from the ChemCam. So, the ChemCam instrument on the Mars Science Laboratory, like I said, as it creates this plasma. So every time we fire the laser, we ablate a little bit in the surface. And so we're actually collecting the spectral response from this location, but as it's fired multiple times in one location, we actually go into the rock a little bit. What one spectrum looks like, there is, the peaks do correspond to certain elements. I think the absolute quantification of this is somewhat difficult, although there are a lot of people who are working on that problem. We typically collect between 30 and 150 shots in a single location. So people analyze this data. So this is just one shot, right? So for every single location, like the corner of this target here, there would actually be, again, this one of these spectra to look at. So it's difficult data for an analyst to look at and say what's going on right here. Nina in particular likes to ask questions like she does not look at one spectrum at a time. What she likes to look at is to zoom in specific wavelengths, very relatively narrow band out of the 5,000 or so that are available. No, for manganese in particular, shot to the next to find these types of dark surface coatings on rocks. Okay, so just to reiterate, her method is first somebody has to, or she has to notice that there's a rock that looks like it has manganese in it. And on that part of it and see what's happening over the 150 shots or so on this example. The approach that I'm taking to try to speed up this whole process is from one shot to the next without zooming in on a particular element. And so I'm able to find, so I did present this at LPSC actually a couple of times already, so I'm not going to go into the details. But the result is that we can see that there is something changing rapidly on the surface of this rock that's numbered from the dark red into the lighter ones of the interior of this rock. Is called Bell Island. That's covered with a lot of dust. And that's pretty much what this is telling us, that there's, I actually take about 10 shots to get through that dust layer. often it's much shallower. Sometimes it can even be a little bit deeper than that. Graphical, this is a probabilistic graphical model. So again, the data here are these spectra. Labels. I don't have any Y values here to match against, but I'm finding that there are specific relationships from one shot to the next. You can zoom in on a plot of all the 30 spectra that were collected on this target. And you can see that something here in this wavelength band is actually it's increasing as we go through the shots. Right. So, in addition to dust layers, there could also be surface coatings. There could be other things that are making that surface shape happen. But again, the idea is to be able to go through the data more quickly than you would be able to otherwise. And so, my plug for what I think the future of data processing should look like, and this is a slide that I presented not to a planetary science crowd, and so you see that this is man-made structures mostly here. The idea is, though, we collect a lot of data. It just keeps on coming. It's not necessarily big by any big data standards, but it keeps coming. We don't always have time to look at it all. We certainly focus a lot on how do we pull information out of here, but there are also humans in here somewhere who are actually looking at the information and labeling things. They might not be labeling things completely in a nice, pretty clean way that you could feed directly back into a machine learning algorithm. But our goal is to actually to come up with more methods to be able to do that. That the people who are actually labeling things sort of on the fly, we could feed that information back into some sort of data to feed into machine learning algorithms that will then get better at actually processing our data. So I'll give you an example of how we're doing this in something planetary science. This is a project that I work on for Department of Homeland Security to look to do forensics and microscopic images of. They want to figure out, for example, where this material come from and what is it. If the person you got it from is not going to tell you those things, put it under a microscope and look at it and circle every single particle in here in green and quantify how big it is and what the shapes are and things like that. This is a very tedious task for somebody to do. We have not yet been able to answer the entire question of just give me an image and I'll tell you where it came from. We can't do that yet. We don't in the next 10 years even. So instead, what we're doing is it's still that a human has to do a lot of work here. We can do an automated segmentation. It's not perfect, so a person has to fix it. Putting things in here and labeling them, again, it's not perfect, so a human has to fix it before we can go on to the final quantification. Very similar problems in planetary science where automation can get us part of the way, but not all of the way. So thinking about a way where you can get almost the right answer, but a person could fix it up, still be the final sort of say in, yes, this is the right way to process the image. So the approach that we've been taking, here's an example image that, again, a person, the goal is to start with this image and outline it. It's probably hard to see from me, but every single one of these particles is outlined in a bright green color. So a person actually has to sit there and make that happen. The method that we use to do it is first come up with an initial segmentation where you can see it's wrong, that there are outlines here that should not be in the middle of a particle. The person does do the segmentation is what we call, there's an over-segmentation. So a segmentation algorithm, and there's a little threshold. They can decide if it's going to be over-segmented or under-segmented. From what we see, over-segments it, because then it's very easy for them to go in and highlight everything in this area and say, should be one segment. So they now fix this one. And now they're going to have to go through and do it for every single one of these and probably remove the things that are too small. This process right here, since we don't think we can improve this in the next 10 years, to go image, like raw data, to labeled answers, even if somebody gave us a whole pile of these segmented images, you could try to do what's called supervised segmentation and learn from all these examples that analysts are doing over time, try to figure out how to do it exactly. yet, but what we are working on is making this part go faster. If these are the segments that you want to merge, we should be able to figure out based on you doing these, that those should also be merged within this particle. Or if you start removing things that are small or are little sticking out on the sides, that as a person is working on an image. Oh, I guess I didn't have a slide on that. But in order to do that, we actually log all the information, all of the actions that a user is taking when they're segmenting an image. And that information is because this is a software tool that's used for forensics. Number one priority is reproducibility. The second priority behind that. As long as you can say, how did a person get this answer? You've met your first goal. Whether or not it's right, we'll worry about that later. So every single action that person takes when using the software is written out to a log on their own local machine. I go around and ask people to hand me their logs, and they do. It also includes a whole pile of bits files, including all these intermediate images, using the person's actions as my data. In order to learn how do they decide which of these things to click on in order to merge them together so that we can go through these steps. So again, I think that there are probably problems in planetary science if we think a little bit more creatively than machine learning tutorials are already out there. They usually want to say, well, we can just start with raw data and go to the final answer. We might need to break it down into steps, and we can solve the intermediate steps. I'll summarize what I think the future of interactive machine learning that I want to hear about other problems that I could work on. It's really hard to go to a planetary science conference where people are talking about the big picture problems that we can be working on is the things that grad students or undergrads spend all summer doing very tedious tasks. Hopefully we can automate some of that. So fully automated analysis is rarely accurate enough, and that's one reason people try something using machine learning. If it doesn't come up with the right answer, you just do it manually. But if you can find an algorithm that gets you close, and then you can fix it, then we can actually reduce the amount of time it takes to get the answer. And then another part that I didn't really give a specific example on, but one other problem that we often find in machine learning is it gives you an answer. For example, you give it an image and it tells you what it thinks is the image. Maybe it gives you the top 5 things it came up with, but they're all wrong. It's not very useful. My probabilistic graphical model tool allows a person to change the parameters of the learning algorithm to data it's looking at on the fly and updating the algorithm. And the reason to do that is because in scientific discovery, you want to look at all possible solutions or all likely solutions, not just the best solution according to the algorithm. That are nearly as good to the algorithm, but you need a way to be able to ask the algorithm what those are. In order to implement the second part, I think it will really require talking to a person who does machine learning and not just taking an off-the-shelf solution that's already out there. There's little interactive hooks in there. So, and then the third one, the example that I gave of using the scientist interaction itself as data for machine learning, and planetary science is well positioned to work pretty heavily on this because there are so many data exploration tools and GUIs available that people are interacting with their data on a daily basis. The hard part will be convincing them to log, put in the code that will log everything a person is doing and then have those people share those workflows in order to accelerate our machine learning algorithms. Those are things I want to think about. I want to hear different problems that we think we can solve with machine learning. Even if we can't solve the big picture, if we break up problems into smaller pieces. I have my own code up on GitHub as soon as I get permission to do so.
Michael, I did last, so I just wanted to comment two things. I think you agree the labeling would be really helpful, and it's a standard problem where do I get the workforce, and I recommend citizen science projects for that. To sell the project nicely, there are thousands of people who love to be involved with any kind of scientific activity. Scratch the career decision and not doing it, but they really GitHub is something where you get a free workforce for. And the other thing, I totally agree with the different difficulty in communicating with each other with this kind of interests. So I have a 90% that we got an HU session for machine learning and planetary science. It comes out any day now, the program, but it's 90% unofficially agreed that we will have a machine learning planetary science HU.
All right.
All right, sweet. So I'm Jay Laura with USGS, presenting on an automated sparse image matching working on this year. This library, if you will, of functionality, but I think the big one is why are we doing this? At USGS, we end up doing a lot of control for the generation of base products, and so being able to automate that is super important to us, especially as we want to be able to scale out the number of that we're using. So for at least a couple of years, I've been hearing about how awesome the CTX mosaic would be. We're not going to do that manually. We need to be able to automate possible. And so the goal here is the automation of that. So the outline, just really briefly, I'm going to talk about what AutoCNet is and what it isn't. I'm going to talk a little bit about where it's hosted. It's open source and totally available. A little about how it works, and the reason the teaser is somehow I got roped into doing a demo tomorrow, so an appetizer, if you will. And then a brief one on why I use it. There's a number of different tools out there, and so what makes this tool or this library different from the existing stuff? So what isn't it? It's not just plop it down and it's going to work for you. It's intentionally designed as a library. For everybody that was in the room next door today, we were talking about different Python libraries in the community and what people are using. These people are using GDAL over and over again. GDAL. Or I guess, how many people in here use GDAL? Okay, sweet. So we all use GDAL because it's a library that has some really nice reference implementations, right? Like they didn't set out to write GDAL translate library and happen to write a really cool reference implementation that was GDAL translate. And so a lot of us are using GDAL as a library to do. Not trying to create an application yet. Now, having said that, we absolutely have a reference implementation, right? Because if I show up with this cookbook with no reference implementation, then you guys are going to be like, what do I do with this? I can't do anything. Reference implementation here is this idea of a graph representation of 13, I believe, CTX images in the Athabasca region of Mars. Each one of these red nodes in the graph is an individual image. There's a potential overlap in between those images. And so the reference implementation basically says, I've got all this nice image correspondence identification functionality. I want to go ahead and put it into something that shows you kind of, and in this case, it's how it works. So I'll show you kind of what happens with that graph in a minute, but for everyone that's on their laptops, if you want, USGS GitHub, it's called It looks like this. It's got all your that tell you that we know what we're doing, or we pretend like we know what we're doing. Read the docs is here. There's some nice user tutorials in there that kind of show you how it works. So that's like reference implementation part 2. The idea being that we have this library, we want to show you how to go about using it. These are all the little tags that again show you that we think we know what we're doing. We've got 93% code coverage, which I would argue is sane for all the 100% projects. I envy you, but I just best to cover things that don't need tests. So we're using Travis continuous integration and app layer, so it'll run on Windows, Mac, Linux. It's all available. Of course, we have OptiKitty up there. So depending on Michael's talk this morning for how do you get it installed, Michael, this is mine. We store stuff on Conda because Content Manager. We can use OpenCV if you really want to. I'm going to advocate not in a little while, but we can. Conda makes it easy to install OpenCV. So as long as you're kind of here in a terminal, you're good to go. And we're hosting a dev package right now. These are all up on the GitHub page, so I'm flipping through. This is basically just a, hey, it's available, it's in Python. So how exactly does it work? So this is going to be like my fly-through of how it works, and then tomorrow I'll actually show you how it works. So this is, what do we got, 9 up there, Apollo 15 metric. I'm going to keep switching data sets to show you that this isn't just like for one data set. We try it on lots of different data sets. Based extraction, so we go to every single node. We can pipe into our cluster with multiple GPUs and be like, everybody take an image and go. And we do the extraction. You can see here the extractor does some really nice stuff. You can tell how it steps through the images, so we get a little higher density up at the top. Still really nice distribution though. 32-bit TV users out there, y'all are even working in 8-bit. So out some of the 32-bit implementations so that you don't have to downsample your data. So here's Themis. Help me out. Night, thank you. The day's really hard, but nighttime. Again, GPU based for the matcher. So this is a KNN matcher happening on the GPU. The reason to go to the GPU for the extractor, you can look at about a minute for a SIF to get the extraction done. On the GPU, we're looking at less than a second. I would say GPUs are totally the way to go. Notebooks, with our reference implementation, this is why I haven't built an application. I really want an analytical environment that's coupled with a library. So this goes back to the last talk, basically, where we want people to be able to interact with the data to understand kind of what's going on. I have fully drank the Kool-Aid, and so we are Pandas data frames all over the place because. So what else are we doing here? Jan-Peter Mueller's group put out a wonderful paper maybe 2 years ago on this coupled decomposition. We're basically recursively partitioning these images based on some initial preliminary matches. We figure out rotation. We go ahead and partition. The idea here is your signal to noise, once you work with really big images, is not going to do anything good for you. And so we have to break these up into smaller problems. We're not making any requirement that we have a priori information, and so we go ahead and we do that via regular standard matcher. I don't know if you can tell that the pretty colors match. All in the right place. When we do have a priori information, it's really nice to use it, right? And so here we're using splice generated footprints. We don't so we don't really have access to their camera models. So we go ahead and figure out a GDAL geotransformation off the footprint, and then we can basically say, hey, these guys overlap in roughly this area because it's an affine transformation, so it's roughly this area. We treat it as such. We're not trying to lie to the user. This is just key point extraction. You can see here differences in albedo do fun things. And CTX is extra fun because the data is super compressed. And this is my why are we doing this in a Jupyter notebook? Why didn't we build an app? One of the classic outlier detection methods that you'll talk about is Lowe's ratio test. Here I'm calling it ambiguity. And so basically Lowe in his paper says 0.8 is a great number. 0.8 is absolutely a great number when it's like your family photos. 0.8 is a terrible number when you're working on these really homogeneous planetary images. I would say 0.9 is my wag in the dark.
with this box plot, 0.9 is going to cut out a huge number of correspondences really early in the outlier detection process. And I wouldn't know that in an app, or I'd have to sit down and write the app functionality. So the idea here is we can basically live inside of this Jupyter notebook for every single edge in that graph that we went back to, generate a box plot, and basically say, you know what, I'm going to apply this ratio check, but I'm going to apply it as a function. I'm going to be under the first quartile, just by way of example. Idea here, another outlier detector. So we've computed symmetry, we've applied those ratio tests, and so now we're computing a maximum likelihood estimated fundamental matrix, and then generate a histogram of that. And so we can see here everything that made it through the fundamental matrix looks really, really good. We're way under 1 pixel. So we're somewhere, we're feature matching still, so we're somewhere in the 1 pixel accuracy world. And it's hugely important because then I can understand what's going on, and I can start to look at, I can look at distributions. Kind of fun. This is Apollo Panoramic. We pulled off of the ASU website. Thank you for whoever digitized those. They're absolutely awesome. And worked with the raw PNG. Did our extraction and all of our outlier detection off of PNGs. Once you get the features out, you're kind of done with the image until you go back to do subpixel analysis. We went ahead and we applied that. Then we can go to the higher res and apply a subpixel matcher, sampled space, and then go to the higher res space. These look really, really nice. And we're kind of finding what's going on. We also, this library also supports, Trent always asks the what about my 40 gig mosaic question. If you really wanted to, you could tile and extract in here if you were desperate to do that. I don't know why you'd want to, but if you wanted to, we can do it for Trent. So sparsity is important. We're not trying to do 3D reconstruction here. I would say, aim stereo pipeline if I want to do 3D reconstruction. For now, I want to do just control. So I want to be able to get to a point where I can bundle. This is a fun little algorithm, suppression via disk covering. It's some arbitrary function. So for all those Python programmers out there, write a cost function, pass it into the suppressor. It then goes through and basically says, this is the highest quality correspondence. I'm going to suppress a disk. I'm going to randomly pick the next strongest, suppress a disk, runs through. It's a heuristic, and so it tries to provide it. So this is how we're able to get good spatial coverage and sparsity, which is important because then the bundle is more tractable. So ISIS is super duper important. We want to be able to work with them. I already said we use their footprint. We also write out an ISIS compatible control network. So that means under the hood, we're generating serial numbers and doing all that stuff. Guys, this is right out of an ISIS application. Just kind of hey, I'm telling the truth. We actually work in ISIS. Also, this is a terrible name. We have wrapped the ISIS 3 bundle classes in Python. Why did we do that? Reading in a residual.csv file and then making it a pandas data frame. I'd rather just have it as a pandas data frame. And so here we can go ahead and we can pipe the bundle off. In that really big gnarly graph at the beginning, we can pull out a minimum cycle, say 3 nodes, just bundle those 3, get the results back, make some decisions about the quality of our correspondences, maybe throw some of those out and then rebundle again. The idea essentially is that bundling is just another outlier detection method in this early context. So why would you want to use this? This is my sales pitch. Almost, why would you want to watch the demo tomorrow? We're GPU enabled, which I think is huge. The CTX stuff, you're just twiddling your thumbs waiting for CPU to extract. So GPU-based is huge. Native 32-bit support, I would argue, is also super important. Otherwise, we're having to go ahead and scale the data. Reference implementation supports distribution. So my background was in parallel computing. It's really nice to be able to take that graph, partition it over a whole bunch of different CPU or GPU cluster nodes, and then chug out on it. Why would you want to do that? CTX, enough data. You're not going to run it on one node. We're loosely coupled with ISIS, so this is a huge boon for us being able to use their bundle adjustment. So thank you to all those developers. We support all the GDAL supported data formats. So the examples I was showing were cubes. TIFFs or PNGs in a world file or whatever you've got. Scalable, so we're able to perform the matching and then stream another image into the graph and say, hey, we just added you. Get yourself integrated in with what's going on. So we're able to constantly stream new data in. So we can start with a small local solution and then add to it. Priority information is super valuable, but it's completely and totally optional. So you can use this for your family photos if you want. Demo tomorrow is the rumor that I heard. It'll be camera models and some other stuff too. Questions?
Quick questions. Python 3.5 apparently is requirement because of OpenCV. Yeah, all right, so not 3.6 yet. And for the, do I need to know anything about it? I have no clue about it.
You need to go to the store and buy an NVIDIA GPU. But otherwise, no. We do dynamic dependency injection for you on the live object. So if you have an NVIDIA GPU, just like running on your CPU, the interfaces are identical. Yeah. Cool. Thanks.
Okay, our next speaker. Scan for planetary and analog sites.
Robert Wagner. I'm going to be talking about a tool we've been testing at OROC for models of planetary sites and Earth analog sites using just sites. So, PhotoScan is a piece of software developed by a company called Agisoft, used to do photogrammetry from arbitrary input images. So it's used in a variety of fields. So archaeologists use it for modeling artifacts they found. Film and TV producers use it for creating models. So a couple examples are in the recent Mad Max film, just to create models of some of those cars so that they could 3D render crash scenes. And there was a fun one in the TV series, The Nick, where they made a 3D model of an actress's face and then digitally cut off her nose, and it looked quite realistic. Modeling, several video games use this to render take measurements of actors' faces to render 3D models of the characters that look realistic. And more on the planetary science side, it's used for aerial mapping of sites like this Italian town in the lower left. And there was an LPSE abstract this year where somebody was using it to try to reconstruct the traverse track of MSL. So the outputs of this software are basically anything you could want that has to do with 3D. So it produces a point cloud of the subject. You can output a 3D model with texturing. You can produce digital elevation models if you have reference points to give it some sense of scale. Photos. And you'll even figure out what the camera model is for the cameras you used for input data. The only thing to note about this is the price. It's cheaper for educational institutes, but still rather expensive. On the other hand, compared to a lot of software like, say, SocketSet, it's cheap. So one through the basic processing sequence, and then we go over some examples we've done where we've looked at how accurate the results are. The interface, and for this walk through the processing sequence, I'm going to be going over the Apollo 11 command module based on a series of pictures we took while it was on display in Smithsonian. So the first step is get your pictures, import them into the program, and just hit align. You don't have to have any a priori positioning information. It will figure out what parts, what images match up to that, what other images, and figure out where they are in 3D space. Now, in some cases, it might not manage that, so this is what happened on this model when we initially images, only the ones on the front side automatically aligned. So there are a few things you can do. Masking out background stuff can help in some cases, although in this case it probably helped that there were background features that you could use to try to align photos. This one work was high points marching around the spaceship, so that each image in turn would get aligned into place. You have all the images aligned, you would optimize alignment function, which figures out the actual camera model and finesses the images into a perfect. And then build the dense point cloud, which is what it uses to produce all of the other products, such as models, DTMs. The advantage of this program is that you have specialized equipment to your data. So a couple weeks ago, we went to SP Crater just north of here to model, and what we used were just smartphone cameras, which are nice because these days a smartphone has a good camera and it has built-in GPS, which the software can use to handle registration data for where the images are, where your model should be on the Earth. Brought along a cheap drone, which helped a little bit, but wasn't necessary for a project. So down here is a couple of calibration markers we put in so that we'd have a scale bar to test this next. So the three projects I got here for this. First, we did a model of a courtyard building on ASU campus. 20-meter square courtyard, and we took a series of images from balconies on that. The final model we just used pictures from the topmost balcony. And that was about 48 pictures. For calibration, we had a couple of markers on the floor. So this is the point cloud it produced after the fact compared to TikTok. And we produced ETM from that, which was a 2.5 centimeter per pixel thing, which is about 3 pixels of input image. And measurements taken off of this across tables and this fountain were accurate to within 2 centimeters compared to what we measured using rulers there. There were some issues where this model was initially tilted north to south, which we had to straighten out by forcing the fountain to be at the same level. So that is something to watch out for. And with small areas, you can tend to have your level not actually be level. Second test site is a bit more applicable to planetary geology. So we took some pictures taken at the Apollo 17 landing site of this trench attachment done in the wall of Shorty crater looking at the volcanic. And this was just a set of 7 images. And for calibration, we used the Apollo node here, which has allows to swing to vertical and a color scale that gives you your orientate or a distance measurement. And we produced a DTM again, which was 1 meter per pixel. and showed that the wall of the trench was about 10 centimeters high, which was comparable to the numbers recorded in the post-mission reports. The model of SP Crater from our field trip a few weeks ago. This was a much larger project. We had several hundred images taken from several cameras and a drone. Basically, I just threw all of that data into PhotoScan, hit go, and it good results. So for scale, this is about a 400-meter wide mountain. This is the Google Earth view of the crater, and this orthophoto produced from PhotoScan. So for this model, we used 434 images from a smartphone, a point-and-shoot camera, and a drone. 1200 pixels. This was about 12 centimeters per pixel. And the absolute elevation and location of this DTM was fairly comparable to the published USGS maps of the location. The difference on this side, just off screen, the highest point we record is about the same location as the USGS topo maps peak recorded height, but it's 7 meters lower. So there may be some offsets here. Comparing to existing topographic data of the area, so here are the two products. There's the shuttle radar topography, 30 meters per pixel on the left, and the USGS 10 meters per pixel right. I'm not sure entirely what's going on with this feature here. It looks like there might be an artifact in USGS data. It doesn't have that little dip in the rim. For reference, here's the DTM we produced to the same resolution as the USGS one, and this video from the drone of the rim. So you can see it's no notches like the USGS data shows. Profile lines across the crater area. Profile from our DTM, dark blue is at full resolution, light blue is downsample to match the USGS topo map. This is the shuttle data, so it shows we have the rims in about the right place and the bottom of the floor in about the right place. Absolute values, it's hard to say because this data is so low resolution. The USGS data, rim peaks are in the right place. We do have some vertical offsets. There's a plot of the offsets with this line being 0. And for some reason they show a flat floor, but that isn't really borne out by either our data or the photographs we took. So I'm not sure what's up with that. In conclusion, PhotoScan is very easy to use. You basically just throw your images in, hit go, and do a few corrections after the fact if it misses some bits. Results, and it can also be used to produce models from existing data on planetary surfaces, like the Apollo images I showed, and probably images from the Mars exploration rovers, MSL, and so on. And just for fun, here's a 3D model I printed based on the data of SP Crater. I will take any questions.
Nice work. I was just wondering how much optimization do you do between your alignments and before you build your dense cloud?
Not especially much. Mostly what we do is make sure that all of the images did get involved in the alignment. I'm not sure how much it does when you hit optimize alignment. The images don't visually move much, but
have you tried doing anything with planetary images? Say, cutting out small sections of multiple areas like
or the Gale?
What we tried is a set of messenger images. So if you saw Ellen Manheim's talk yesterday morning, I took the images from her Sandra Crater mosaic and just threw them in. And it produced something that looked like a GTM, except it was inverted and the images were placed inside where I think Mercury is. Not figuring that.
Thank you. Real quick, just wondering what years or how long ago were those other PDMs, USGS, PDM, shuttle radar?
I do not. Shuttle radar was 90s. USGS PDM, I cannot tell. Their metadata on that doesn't specify.
Discrepancy due to erosion.
Probably not much. It looks like the rim is a fairly solid rock. There's definitely some erosion, but it's just little rocks falling off the side.
Because you did some handful. When was it loaded? Today? Earlier today?
Switch to.
Because we can do. Oh. Oh, you.
Yeah.
Single one position. Single offset.
Our next talk is with Tyler Thompson here, extracting computer shaped information from narrow angle.
Hey, I'm Tyler Thompson. I'm here to present on how we did a study about crater morphology on Apollo sites. So I just want to walk through the methodology and the tools that we developed to do that. So craters, if you look in the top right, small lunar craters start with a visible ejecta, relatively crisp shape. Over time, the ejecta wears away, and eventually, as you progress to a more and more degraded crater over time through micrometeorite impact, shaking, or other degradation mechanisms, shallows out until it's difficult to identify the rim. So qualitative classification system is just A, B, and C, where A is the freshest crater, B is intermediate, and then C is the most degraded crater. For the size range of craters that we were looking at, 30 and 300 meters, they're actually sensitive to target properties. So the strength and cohesiveness of the geologic unit, the impact can actually affect how quickly the crater degrades. We used some of the old pre-mission maps. So the Apollo 16 map of the Descartes region from Hodges and Apollo 17 from Ruchita. And we generalized those into certain terrains. And we wanted to compare the crater morphology both in terms of qualitative classification and quantitative shape-based classification, whether or not there was a difference between the plains areas and the mountainous areas between comparable sites, like the plains in each site. So I'll walk you through that methodology. But for the size range of 30 to 300 meter craters, you really need to use the narrow angle camera DTMs, which have a scale roughly between 2 and 5 meters. These observations are targeted, interesting, or important sites, so naturally the Apollo sites already have a really nice mosaic associated with them. We went through and digitized all of the Apollo landing sites. for craters between 30 and 300 meters to extract the topography to do these type of studies. So in general, we're trying to go from having go through and scan these images, DTMs, slope maps, hill shades, and identify crater data sets. Use ArcGIS, the NISO 3-point crater tools and ArcMap. You can use click the center and drag to the rim polygon approximations of circles from plugins in QGIS that could output a circle or a polygon shapefile, basically, where you're looking at these craters. And we're trying to go from these digitized data sets, these high resolution DTMs and images, and extract shape metrics, things like how steep are the walls, what's the depth to diameter ratio, is the curvature of the rim. So we're trying to extract these uniquely for each of these individual craters that we find within our study areas. And with the digitization of these old pre-mission maps, we want to compare some of these shape metrics in regions for Apollo 16 and 17 or the mountainous areas for those sites to see if the median wall slope, so how sloped the midpoint of the wall is at a particular baseline, to see if that's different. Material properties are affecting the degradation. So here's just the general workflow. We start with feature logging. We have we cross-check each other. So multiple people will go through the data set a couple of times. We'll generate a shapefile. We'll extract the topography and imagery, qualitative classification, and we'll do a quantitative classification and eventually be able to do statistics and stuff to compare. So I'm going to start with just talking about our feature logging approach. So like I said, we bring in multiple types of data for each of the sites that we're looking at. It is all overlay a minimum size grid and a maximum size grid on top of the study area. So on the left, you can see the blue lines are 30 meters and the pink lines are 300 meters. And the thick black line is the click and drag highlight in QGIS to produce a polygon approximating that circle from your click and drag. That's from the Apollo 17 site. One of the things that helps me as I scan through the data set is just to do the slope map, because if there's a concentric area with 10-degree slope, it's likely that that's, so that'll help you pick out the easiest ones first, and then you could go into like high incidence imagery or hill shades from different directions to pick out the ones that aren't quite at 10 degrees and wouldn't show up in the color session you have for the slope. Products helps you extract the features. So the next thing I'm going to go over is how we correct for asymmetry when we extract the topography, and how we kind of find the best fit for the rim position, because the visual click and drag doesn't always tell the whole story. All right, so you start in the top left, figure A, with the identification of the crater. Just a simple case, it's probably a degraded crater at one of these sites. Make the rim with one of those tools that I mentioned in your GIS software of choice. We have some MATLAB code that pulls in the DTM and the image where they overlay perfectly pixel by pixel to extract a certain width of image and DTM. In our case, we did 3 times the diameter of the crater. So a diameter to the left, a diameter to the top, to the right, to the bottom. So we have a diameter everywhere around the outer edge of the crater. So we take in that image data and that DTM data, kind of 3D data, where you can drape the image on top of the DTM. The new is start at the center of the crater and travel in every azimuth outward from the center of the crater to where you approximated the rim, and find the best position for the rim. So where it's rounding off, where the slope ends up being 0, where the or something. And each one of those points, either if you look at the black dots in figure D or the blue dots in figure C, is an optimized rim position along an azimuthal vector outwards from the center of the crater. What we do is a circle fit to those vectors. Figure E, which is kind of the best fit circular approximation of the crater, correcting for general topography and stuff. So if there's a baseline slope or a 2D plane, a 3D plane that you could fit to it or something. And in the end, you could average all of those vectors from each direction, and you could have a mean crater profile, and you could have that for every crater in your data set. You could figure out how asymmetrical they are. You could do all sorts of statistics to try to figure out the shape of these craters, how unique they are, how symmetrical they are, how unsymmetrical they are. Example of the tool that helps us how to get that data. So you can click and drag and rotate the actual 3D topography that you extracted and where the best fit rim projected onto that is at the current time. Sometimes, because if the topography is really irregular, you'll end up with a rim that's pushed off really to one side along one set of those azimuthal vectors will fit off. So you actually have the option of we're expanding it out for the rare cases where the optimization algorithm doesn't actually give you a good result. All right, so the last thing I want to talk about is just the visual classification. This is based off of a degradation classification scheme that's already in the literature, produced by Vasilevsky and all. The ABC classification, me and a colleague or two will go through the data set and actually visually classify every one of the craters based on their. We can later compare that with the quantitative metrics, like how steep are the walls of those craters and how sharp are the rims of those craters and such. So combine both the quantitative and the qualitative data and see how things are getting classified. Of wall slopes are that actually give you something that looks sharp to your eye or not. A little tool that we had to make that whole process go a lot quicker instead of scanning around in a GIS or something. So it's literally just selecting the button for what you think the classification is. And the cool thing is that we can cross-check each other and so going through all of this, we have about 14,000 craters from all the Apollo regions. We have a couple of studies and posters and abstracts out that have come from the comparison of plains units in different areas of the moon, or the comparison between plains units and mountainous units and such. So into different types of geology, so like volcanic trends and stuff. So stay tuned for more interesting results as we study the morphology of the small craters. All right, any questions?
Hi, Raquel JPL. Interesting work. I look at craters. Have you considered just using the dam itself to automatically extract craters? Crater's a watershed, right? Yeah. And everything would pour into it. If you just wanted to pick the center of a crater, rather than use that center point as like as the have the crater, you fill it automatically extract the actual, and then be able to collect statistics along it.
Yeah. Well, as I went through and digitized those 14,000 craters, I definitely thought that, or at least hoped there was a better way. And especially like these ways that people have come up with to have the machine do it easier. Be good to get out of the student worker role of doing it manually. But it's got some good algorithms. Thanks. Yeah.
Any other questions?
Trace the They're modified, yeah, but it's still.
So our next talk is going to be improved access to Kikuya hyperspectral data, and it's a joint mission.
I'm Michaela Shepard.
And I'm Zoe Hobart.
And we did this as a year-long project for our final project for our bachelor's degree. And we did it with the USGS astrogeology. And so what we did was we improved access to the Kikuya hyperspectral image data with the spectral profiler on Kikuya. As I just said, the data that we worked with was the spectral profiler on Kikuya, which is approximately 4 terabytes. And so it's very hard to work with the entire data set at once unless you want to download the whole thing. This instrument actually provides the hyperspectral imaging, and it's a lunar orbiter that JAXA launched. And so the current methodology to actually work with this data is you go to the Selene Data Archive, you input textual parameters, and results come up, and they're all aggregated by image. And there are several problems with this. So number one, because these are hyperspectral data points, it's much more logical to actually work with them on a latitude and longitude basis, because each one of them has a latitude and longitude associated with them. Lots of metadata associated with it, but currently to actually access these points, you have to download individual images, and there isn't map-based searching, so you have to input your parameters, and what comes up, and then you download each of these images and load them into QGIS to actually work with them.
So our project's focus was to improve the access to this data set. And using a tool that we call the Kikuya Spectral Profiler Explorer, or Casper, software system. This software system was built on standardized technologies and a modern web stack. We built it using a 3-layer architecture that streams data, large amounts of data through the system dynamically. Our solution provides map-based contextual search, allowing for the exploratory data analysis of this data set. Our clients want a solution that could both visualize the geospatial data as well as the specific hyperspectral data associated with these points, as currently you have to do that separately and manually. Technologies that our system makes use of: MongoDB. MongoDB is a non-relational database system. We selected this system scalability. It provides easy horizontal scalability. So the intention is for this to be run on a cluster of GPUs, allowing for reads of this data set. And it also supports geospatial queries and spatial indexing, which was also a desirable trait. We're also using GeoServer, which is a software serving application, which allows us to publish our data in OGC compliant formats, such as webmap servers or WMS. Node.js, the JavaScript runtime, to build a application server. This application server services to the front end of Python scripts to do such things as to generate new image data as the user changes the query on the fly. Finally, Leaflet is used on the front end. Leaflet is a JavaScript mapping to create dynamic and customizable maps. So this is a brief overview of our architecture. As I stated earlier, into 3 sections. The backend is the MongoDB database instance, along with the GeoServer server, which publishes the map tiles for the front end to consume. This is our Node.js-based application server, which uses Data Shader, which is a library for creating visualizations of large amounts of data as images, and GSconfig to create those layers as map layers in GeoServer that can then be published and consumed by the front end. Finally, the client is a front-end JavaScript application that uses Leaflet to create an interface and interact with this data set. through contextual map-based search. So in order to deliver this data and visualize it for the user, there are kind of two different approaches, obviously, for displaying image data. Now layers, which allow us to define geometries exactly, because it gives us large amounts of detail and we can make these points interactive. However, the downside is that we can't encapsulate large amounts of data, as that would overload the system and the amount of data going over the wire. The other option is to use rasterized layers, where the data is summarized into discrete pixels, showing a global view of the data. However, we don't get the amount of resolution that we do there. So we actually have a quick video demo here. Hopefully it'll work.
So there's kind of a still of it. Sorry, we had a video. So you can kind of see it's actually kind of blurry, but there is basic things that you see on like any map. So like in Google Maps, you have a plus and minus for zooming in and out. On the top are 3 boxes. The top 2 latitude and longitude, so you actually can manually enter the latitude and longitude you want to look at. The one on the bottom is a layer changing. So for this, we're actually looking at the terrain camera on Kaguya is the base of it, but if you wanted to look at anything, let's say Lola on the bottom, you can actually change it. The red dots that you see are actually the hyperspectral points associated with it.
Yeah, so as I mentioned earlier, we're displaying data in 2 different ways here. As Michaela's mentioned, the red dots are the points that displayed as a vector layer. So these are interactive. We can click on them, and once we click on a point, we asynchronously request the hyperspectral data associated with that point, which will then be displayed as a graph. The blue and orange dots are the data set displayed as a rasterized layer. This is computed using the Python library data shader. What we are doing here is we are binning the points into individual pixels. These pixels are assigned a color value based on the recorded intensity at a specified wavelength.
So something that you couldn't see in the other video because it wasn't working is at the bottom there, when you actually click on a red point, there is a graph that as you scroll over it, it'll actually tell you the reflectance value at a particular wavelength. You'll get like 300 different wavelengths. And as you click on different points, it will actually update this graph according to the point that you're actually looking at. What we did was we created Casper, which is a web application that allows for exploratory data analysis. We automatically plot the hyperspectral data associated with a particular point. And in addition to that, you can actually change the base layer associated with it. Oh, sorry, that's .gov for me.
She doesn't really work for us.
Yeah.
You want to try to get the video over to me?
Oh, we can? Okay.
Do you want to connect to the internet?
Yeah.
Oh, sorry. You would have been in.
Well, anyway, you can go to our GitHub and download it. And the data set that we were actually working with for this was actually 40 gigs, but because we use MongoDB, it could actually be horizontally scalable to actually include the entire Kaguya data set, or data set you want.
Thank you, guys.
Talk of the session here.
Nope.
Yeah, sure. Okay, final talk of this session is Kirsten.
Yeah.
MoonDB update on the restoration.
Okay, I think this is switching the topic, but maybe for the final topics, everybody else. Hopefully. So I wanted to give an update on our project that we have funded through the PDW program 2 years ago with the focus on restoring and synthesizing data that has been generated on the Apollo samples. Collaboration between the Geoinformatics Research Group at the Lamont Doherty Earth Observatory of Columbia University and Johnson Space Center Group. So the goals of this project have been to ensure that all the data that over decades has been generated by studying the lunar samples in the lab by PIs in and others, and to make them accessible and make them more reusable. They currently very distributed throughout the literature. Many of the data has actually never been published. Some are summarized in the Lunar Compendium, but it's been a concern of the community to access these data. Just to summarize the goals, it was, really maximizing the scientific impact of these data, but also thinking about the future, because these samples are still getting used in new studies, and that data gets integrated with what has been produced in the past. We have to think about the limited resource that we have with these lunar samples, and we wanted the analysis handing out new samples if there is data already accessible. There was a different slide in between, but maybe not. The deliverable, so to say, of the project is building this database, MoonDB, with a search interface for users to retrieve, to explore the data, but also do really go through the whole literature of the last 40 years and compile as much as possible the data that exists already. And then we had a component of trying to engage especially senior researchers who are either already retired or close to retirement, who generated lots of data in the 1970s and 80s, to get them and hand us over data that they still have on their computers or in their DRAWs. This was supported by the folks down at the Johnson Space Center who curate the samples and have helped us with technical advice and so on. And they run databases that we clearly want to link up with this compilation of the sample data. Now, we didn't start building this from scratch. We actually, I'm directing a data facility that is funded by the National Science Foundation and deals with terrestrial sample data. at least, and that's the EarthChem suite of systems. We have a data repository called the EarthChem Library that curates data, publishes them, DOI assignment, and the whole suite of repository services. And then we have already developed and operated the synthesis database called PDB, which synthesizes and petrological data for terrestrial samples. And that has provided us with a data model with curation workflows and user interface designs that we were building on. The challenges we've had with the project is that this PDB database actually started to a new data model. And that has caused some delays actually with the MoonDB development because we had unanticipated challenges with this new data model. Get to that. Just to show you a little bit of how the repository and the synthesis database in the EarthChem facility work together. Does this actually? No. Okay. But when you look at the middle line here, investigators, they submit their data sets to the repository, to the EarthChem library. We have a whole process implemented that looks at the metadata, but also into the data themselves, looks how well they documented with respect to provenance information and so on. And then from these are usually spreadsheets. The geochemistry community works with Excel spreadsheets primarily. Spreadsheets, we're actually ingesting data into a relational database. That is the synthesis. And that's what MoonDB really provides. So as I said, this PDB database really served as the role model for MoonDB because we've had a long history of very successfully supporting science for geochemistry and petrology that has been growing to now over 100,000 samples from ocean floor data and so on. Is really heavily used for new studies, for actually new approaches in our field in geochemistry, trying to work for the first time with huge quantities of data to discover patterns that before was not possible. So we envisioned that the MoonDB will facilitate a new level of mining these lunar sample data. Really, we're taking these spreadsheets apart and allowing access to individual values from individual measurements of data sets. And all these individual measurements are linked to the context and to provenance metadata, which allows for a very sophisticated way of filtering the data, searching the data. We also make a big effort to harmonize the metadata, classification of rocks, and the features of interest that are described. And then we provide tools that allow investigators to extract subsets of the data that they customize, where they again synthesize across different sets, and they can download these spreadsheets then in a way that they can immediately work with it. An important aspect is that we use unique identifiers of samples that allow us to link data from studies that have happened over many years or decades. And so this is the current status of MoonDB. We have built the database, as I mentioned. It's using a new data model called the observation data model. I have a second slide on that. The model has a very complex structure. Index it very well, and we have been using Elasticsearch for full text searches and data, but we're not happy with it. I'm going to get to that. An API that's used by our search interface, but will be made public so that others can have direct access to the database. We have a first prototype of the search interface and PHP scripts for loading the data from the spreadsheets into the database. As I said, this observation data model is fairly recent, was developed through a collaboration between hydroinformatics people, people working on soil sciences, and people working in the igneous rock world. And it had the intention to integrate time series with sample-based data. And that made it very generic and very difficult to use for building interfaces, for building loading tools, and so on. So we've gained some experiences with this, trying to stick with it as much as we can. An important aspect is that this observation data model is actually the observation and measurements model from OGC, the ISO 19156. As I said, we have encountered these technology challenges, which keeps us in the mode of reviewing and optimizing technology and potentially moving to other solutions. Down here, we're trying to figure out if material views works better for us than the Elasticsearch. With the ODM, we had expected also to take advantage much more of other tools that have been developed, but everybody does their own little different implementation, and so that hasn't quite worked the way we had expected. But we have this interface. As you see, it looks like the typical faceted searches, where you can filter based on, at the moment, based on the Apollo mission, on interest, on authors, on classification of the rock types, and so on. Of the samples for which data exists. We have included all samples that exist at the Johnson Space Center. That shows just identification, but if you actually get samples for which results are available, you see this in this list. The sample profile pages basically that give you all the information that the database has about these samples. An important aspect here, related samples, we actually track the relationship between the hierarchies of subsamples that have been handed out at the repository, which will give us a lot of options later to compile and to integrate the various data sets. There's a lot of outstanding tasks. Obviously, still the next thing we want to do is get some members of the community to test and provide feedback on the prototype. An important activity that we're developing at the moment is the search by chemistry, where people, give me all the lunar basalts that have less than 0.2% titanium and so on. We need to still implement the tools for downloading the customized data sets. Technology obviously did the linkages, center systems, and one of the aspects here is that they need to implement persistent unique identifiers for samples, the International Geosample Number. There was a report actually at the last AGU meeting already about that. With respect to the data compilation, we have compiled data from over 700 papers now. 200 of these are already in the database, but we stopped ingestion in order to solve some of the technology issues first. We have started digitizing of older reports. There are more to come. They are published in the EarthChem library and become citable. And you can see they have, everything that hadn't been published before, those data sets have been basically deposited into the EarthChem library. They have DOIs for citing. They are linked to literature if that's possible. We're actually getting a lot of data sets these days now through the literature, because increasingly publishers demand that data be deposited in public repositories. So even meteorites are coming into the EarthChem library now. and this is just a screenshot, I can skip about that. We held a workshop in 2016 at the Lunar and Planetary Science Conference, and investigators there really wanted their own data submission site, so we have set this up. This will be released in about 2 weeks, so it gives the feeling, it goes into the EarthChem library, but it's sort of the MoonDB for the website. A reference catalog. This is a catalog of all the references with lunar chemical data that existed already at the Johnson Space Center and that has been added on now with the compiled data sets that we have. What hasn't worked so well, unfortunately, was our effort to rescue data from investigators. Even though there was a group of nearly 10 investigators who enthusiastically signed up initially to this project, we've had a really, really hard time motivating them and getting their attention into publishing their data. We've offered resources, be it money, be it interns. So, hopefully, once we can demo the usability, the utility of the system, there will be more movement. But this is, if you have similar experiences, I would be more than happy to learn how to improve the status of these contributions. To go from here, I mean, we obviously want to make the user interface fully functional with all the capabilities that that the investigators want. One thing I realized being here is that we need to make a bigger effort to better connect and integrate with the PDS, possibly run another data rescue campaign. We've had feedback at this workshop at LPSC also that people want geochronology data are excluded. So there's obviously a lot of geochronology data. We're going to be working with other investigators on achieving that. And there has also been some feedback in saying why not include meteorites and so on. So those are things to explore into the future, and we're going to be looking for feedback as much as possible. Thank you.
Comments. First of all, thanks for coming back and sharing this with you after 2015.
It didn't work out.
Yeah. So one question is, are you envision this kind of thing for archiving or supporting data from terrestrial analog kinds of materials? And many of those are still being collected actively. And so this, as a repository, this might be a good place to put some of those data that are being funded by current.
I mean, I think a great opportunity in that, the data we have in PDB and in similar databases can very easily be integrated what one goes into MoonDB now. So it will be great to compare persons, and it was actually in part the initiation of the project where those investigators who were terrestrial and lunar samples and said, we have PDB, why don't we have MoonDB? So there's a lot of potential to include more data and very targeted those type of data that would support or in some way is in MoonDB.
Thanks everyone for being here this afternoon. Thank you, Dan. Thank you, Lynn, again. An entire day of support. We really appreciate your help today. I want to remind people, stick around for a few minutes and be part of our group photo if you can, if you have an interest. I know a lot of people have already moved on this afternoon. I'm just assuming they're going to be right back to the photo. So anyway, we're going to meet in the lobby here by the staircase in a few minutes.